Hello and welcome to the final part of this chapter, and actually the final part of all of Further Mechanics 1. And now we're going to be looking at 2D collisions, or what we call oblique collisions, now with two particles rather than just a wall. Okay. Now before we get into it, again I must emphasise that this is year 2 or year 13 content only. So if you're doing AS or half the course, you don't need to worry about it. But anyway. So what we're going to be looking at, right? So two things collide. Now we've already looked at that in chapter 4 in year 1 with 1D collisions, right? Now the idea is with 2D collisions, obviously you've got 2 dimensions, and obviously we've got this diagram here. Now what's happening is we've got, say, for example, let's say we have 2 particles, right, or spheres. They're going to move towards each other like that, and then they're going to get even closer. And then eventually they're just going to collide, okay, like that, okay. Then they're going to separate, right? So then after they collide, they're going to then move like that, right? And then they're going to go like that. That is generally the gist, right? I hope you can see that, right? So at the absolute instant when they do collide and meet each other, that's what we're interested in. That's what this diagram is doing here, okay? Now, when two things meet, now the main thing really to consider is when we have 2 balls or 2 spheres meet, we draw what we call a line of center. So obviously these spheres have centers, right? Now, when we draw the absolute instant when they collide, we draw a line like this, and that's what we call the line of center. That's going to be crucial for these questions, okay? Oh, sorry, not line of crucial, line of center. What was it thinking there? But it's going to be crucial to recognize this for questions, right? I'm not going to bang much longer on this. I want to jump into examples because I think it's the best way to understand this. But the last point I'm going to make is that everything acts what we call parallel to the line of center. Everything acts along the line of center. So what I mean by that is momentum and restitution and impulse. So this I here is the impulse, okay? So what I'm going to say is everything acts parallel, or I'm going to say along the line of center, okay? So that includes momentum, restitution, and impulse. Okay. And again, you'll be familiar with all of these from 1D collisions. And actually, this is basically just going to turn into a glorified 1D collision situation. It's basically just a fancy 1D collision problem, essentially. You're going to see that in the question in a moment, what I mean by that, because everything acts in one direction pretty much. So we can basically just transform the problem to one dimension to find what we need, okay? Okay, let's have a look at some questions then. So I've got this question here first, okay? So obviously I've got this diagram here, and it says a small smooth sphere A of mass 1 collides with a small smooth sphere B of mass 2. Just before the impact, A is moving with speed 4, which you can see here, in a direction of 45 degrees to the line of centers, and B is moving with speed 3 at an angle 60 to the line of centers. Coefficient restitution is 3/4. And so what's for me to find the kinetic energy loss. Now, before we start worrying about kinetic energy and stuff like that, the main idea is, again, we want to draw the situation out. And I'm going to recommend you just draw a bigger diagram, okay? Because that's not going to be enough room. So I'm going to draw an absolute massive sphere like this and this, okay? And so, okay. So I'm going to draw the initial information on. So obviously, okay, well, firstly, we've got the line of centers, right? So the line that goes through the middle, like that, okay? Now, that's what everything's going to be connected to. So obviously, for A, I've got the speed at an angle 45 like that. So I'm just going to draw it like that. There we are. There we are. And then I'm going to call that A then, right? So that's A with mass 1. And then for B, well, now it's going up. It's going with speed 3 at an angle 60 like that. So if I draw that on, there we are, right? So it's going to be B of mass 2. And there we are. So that's all the information we're given. Now, obviously they're going to collide, right? And if you can imagine it, if A is going to move like this, it's going to rebound at a speed like that. Okay, hopefully you can see that. That's the direction A is going to go. Likewise, B, you can imagine, is going to rebound like that. Okay, hopefully you can visualize that, right? And so there we are. Right, now, again, what we're going to do, again, like with collisions with a wall, like last time, we'll want to split the components up. Now, I'm going to do this in a very specific way because it's very easy to get really messy workings and a really messy diagram. So I'm going to draw out my information like this, okay? So again, the idea is I want to do it parallel and perpendicular, okay? So it's going to go up like this and then across like that, right? So this is going to be 4 sine 45, that component, and then this would be 4 cos 45. Okay, hopefully you're happy with that. I'm splitting up the speed 4 here, again, into horizontal, vertical, or parallel and perpendicular parts. Hopefully happy with that. Now what I'm going to do instead is, I'm going to move this component. I'm gonna write it like that down here. So down here of 4 cos 45. You're gonna see why I'm gonna do that in a second. So I'm gonna just move that part down here out the way. Okay. So those are my two components. Now, as for after the collision, so I've extended this by the way a little bit. Now after the collision, obviously the speed will look like that. So if we was to do that, we would have to go along here, then up here, right, to match this speed there. Okay, now usually what we'd say is that we'd give this a speed v, then an angle alpha, then this would be like v angle alpha here, then this part horizontally would be v cos alpha, and then here of v sine alpha, right? If I make this a bit neater. But two things. First of all, we're actually not going to include the angle or the speed here, okay? And again, you're going to see why when we tackle the question. I'm not going to even bother mentioning a speed or an angle. I'm just going to split up the components. So we're going to go across here, then up here, okay? Now, the second thing to note is that the perpendicular, or the perpendicular part, so perpendicular to the line of centre, is going to be these two components here, right? The v sine alpha and 4 sine 45 are perpendicular, right? Again, hopefully you can see it, because they're at right angles to the line of centre, right? In the middle. So the perpendicular components. Now, perpendicular components don't change. Don't get that confused. I'm going to write it here. Don't get that confused with collisions with walls, because with walls, it's the parallel parts that don't change. But in this case, the perpendicular components don't change when it's with two balls, right? So what we can say is, because the perpendicular parts don't change, if this was the original perpendicular part of 4 sine 45, it's still going to be 4 sine 45 afterwards. Okay, there. So I could just immediately just add that on. Okay. Now, the last thing to note is, okay, again, yes, we got rid of the speed and the angle. So this component, again, like with here, I'm just going to bring that up here, okay? And now that would be v cos alpha, right? If we was to include a speed and an angle. So if we had v and alpha, but I'm going to get rid of my angles and my speed. I'm just going to give this a letter, right? I'm just going to call it, let's say v, okay? Like that, okay? So I'm not saying v cos alpha, I'm just literally saying v, okay? So that's the horizontal component. I'm not giving it an angle. I'm just going to call it v, okay? Because if I was to call it v cos alpha and include an angle, I'm introducing two different variables here, v and alpha. But actually, if I just shorten it to just v, then it reduces it to just one unknown. Okay, so that makes the problem solvable, essentially. Right, a lot going on there, okay, but that's how I want to set this up. I'm now going to do the same for B. So again, this is going to be my speed initially. So if we were to do the components, we'd go up and then across, but actually I'm going to do that down here, okay, like that. So this part, so this is going to be 3 sine 60, okay. And then this part's going to be 3 cos 60. Okay. Then afterwards, okay, again, we'll then go across, then up like that. So if we go up, well, it's going to be the perpendicular component. So it's going to be 3 sine 60 as well. And then I'm going to bring that and then just bring it on top like that. And I'm going to call that different letter W. Okay, let's say. And so those are all my components, right? Right, so that's how I'm going to want to do these questions, right? Again, it's probably a bit confusing the first time around about having to lay it all out. But hopefully with a bit of practice, it makes sense. I've laid it out again for a very particular reason. In the long run, you'll see it helps to lay it out like this, okay? But anyway, so that's the perpendicular component. So what about the parallel? Okay, so obviously what do we want to find? We want to find the parallel or the horizontal parts W and V here afterwards. That's what we want to find, okay? That'll give me my speeds at the end. Now, for the parallel parts, okay, as I discussed, that's where everything's going to be involved, your restitution and your momentum. Now, actually, what we can do is, because everything acts parallel, we can just redraw the diagram A and B like this, okay? And you'll be very familiar, this is how we draw 1D collisions, right? So A has mass 1 and B has mass 2, I believe. And what I'm going to do then, right, I'm just going to do my parallel speeds. So if I look at the diagram before, for A, it's going forward here by 4 cos 45. That's the parallel part, right? That matches the line of centres. It's going like that. For B, well, the parallel part is 3 cos 60 going to the left. So for A then, if I copy the parallel speeds, 4 cos 45. And then for B, it's going backwards by 3 cos 60. And hopefully you start to see it very familiar. It'll turn into a 1D collision problem. Okay, then afterwards, as I discussed, then we said that the parallel speed is V going backwards, and for B is going W forwards. Okay, so I'm going to add that on, and hopefully you can see it will turn. It's just a standard 1D collision problem at that point. That's what the problem just boils down to. Okay, so that's why I said it's just a glorified 1D collision situation, essentially, right? This is so that we can find the speeds V and W here, right? Using normal techniques. So momentum, if we were to apply it here, okay. We have all the ingredients here. So it's for A, it's going to be mass 1 times velocity U cos 45. No, 4 cos 45. Sorry, it's a 4, not a U. There we are, 4 cos 45 there. Then for B, then it's going to be 2, and then well, it'd be 3 cos 60, but usually we take forwards as positive, okay? So it's going backwards in the negative direction, so we need to negate that, okay? And so then afterwards, the momentums afterwards, well, it's going to be 1 lots of minus v, and then 2 lots of w. Okay, hopefully happy with how with this momentum here. So it's just literally how we do momentum with 1D collisions, right? And we can simplify this equation. So we're going to get minus v add 2w to be minus 3 add 2 root 2. Okay, in exact form, but actually the answer doesn't mind decimals here because you're going to get quite nasty numbers. So if I just give that as a decimal, that is minus 0.172. Okay, and so that's my first equation there. Hopefully happy with that. So it's just a standard way we work out momentum from 1D collisions, right? Exactly the same process. We're also going to do restitution in the same way as well. So E, now the way I do it, and I've done many videos working at restitution from chapter 4, but the way I do it is v2 take away v1 over u1 take away u2. This formula here, this formula makes it very safe, so there's no second guessing with anything. Anyway, so if I was to calculate E here, well, v2 is w, take away v1. Now v1 is v, but it's going to be minus v because it's in the negative direction, right? Then u1 is 4 cos 45 and u2 is 3 cos 60. So 4 cos 45 take away 3 cos 60, but that's in the negative direction, so we're going to negate that, okay? And there we are. So if we simplify this, we're going to get w plus v. Now 4 cos 45, 4 cos 45 plus 3 cos 60. That's not a nice number. It's a half of 3 plus 4 root 2. That's what the calculator gets me. And there we are. So E, now we're told E in the question, E, the coefficient restitution is 3 over 4. So that means this is equal to 3 over 4. So W plus V over this whole number here. And so therefore, if we times across, we get W plus V to be as a decimal 3.246. Okay, and that's my second equation there. Okay, so hopefully happy with that. So just doing momentum and restitution in 1D. Okay, so it's the same sort of techniques. So I've got these simultaneous equations. So W plus V is 3.246, and also 2W minus V is minus 0.172. So again, I can solve these simultaneous equations, even just think about the GCSE. So I can add them to get rid of the V's. So 3W then is going to be 3.074, blah, blah, blah. So if I divide by 3, I get W to be 1.02 to 2 decimal places. Okay, that's my speed W there. Then to find V, I'm going to substitute W back into one of the equations. Let's say I do it into that one. So sub W into W plus V is 3.246. Therefore, 1.02 and V is 3.246. So therefore V, subtract 1.02. We get 2.22. Okay, and there we are. That's my speed V. So we found all our speeds, right? So there we are. Hopefully happy with that. So this portion is just again standard 1D collisions, right? From AS. But there we are. So hopefully that makes sense. So what's it want me to find? It wants me to find the kinetic energy lost. Now, I'm immediately thinking of the formula, right? So the loss in kinetic energy is always, with collisions, going to be the kinetic energy before, take away the kinetic energy after, right? So if we work this out individually, so the kinetic energy before the collision, firstly, and again, it's going to be very similar to 1D collisions. Now, before the collision, they've actually given me the speeds quite nicely. For A, originally the speed is 4. So the mass is 1. So for A, before, kinetic energy is half times 1 times 4 squared. Okay. Hopefully that makes sense. Then I can do the same for B. So the speed before is 3, okay, and the mass is 2. So it's going to be half times 2 times 3 squared for B initially, okay. And so if you work that out, you should get 17 joules. And there we are. Then what about the kinetic energy afterwards? Okay. So the kinetic energy afterwards. So for A, okay, afterwards the speed, well, it's going to be that sort of length there, that sort of hypotenuse, right? Now we know what V and W are. V was 2.22 and W was 1.02, right? So I can add that on if you want. Now for A then, well, the speed. So I want to work out the speed here. Now I've got the other two sides, right? I've got 4 sine 45 here and 2.22, which I've worked out there. And so it's going to be sort of the hypotenuse, right? If I was to construct the triangle, right, it would look a bit like this. So that'd be my speed. And then I've got these two lengths here. So 2.22 and 4 sine 45. Hopefully you can see then that I can do Pythagoras to work out the speed. So I'm going to do 4 sine 45 squared and 2.22 squared and then root it, okay? So that's what I'm going to do. So I'm going to do it down here. So the speed of A afterwards is going to be the root of 4 sine 45 and 2.22 squared. Now if I work that out, I get 3.596 meters per second, okay? And then I can do the same for B, right? So if I look back at my diagram, for B, again, this will be my speed, but again, I got the other two sides, 1.02 and 3 sine 60, so I can square those two components to get my speed, right? So 3 sine 60 squared and 1.02 squared. If I work that out, I get 2.791 meters per second there. Okay, so hopefully happy with that. So that's my speeds. So therefore, with the kinetic energy afterwards, well, for A, well, it's going to be half lots of the mass of 1, then the speed, which is 3.596 squared. Then for B, it's going to be half lots of the mass of 2, and then 2.791 squared. And so if I work all of that out then, I get 14.255 blah 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 joules. Okay, so I've got my two kinetic energies before and after, therefore I can use my formula to work out the loss in the kinetic energy. So before is 17, take away afterwards, which is this 14.255. So if I work that out, I get 2.74 joules to 2 decimal places there. Okay, and there we are. Now for part B, it's asking for the magnitude of the impulse exerted by A on B, or in other words, basically the impulse occurring here. Now, as I discussed at the start, impulse also acts parallel. So again, I can consider my 1D diagram, right? My parallel diagram here. And so again, how do we deal with impulse in one direction? Well, A is going to push into B like that. So B will receive an impulse here. Likewise, B will push into A like that. So A will receive an impulse there. Okay. And so it doesn't really matter which diagram, which sphere we consider here. It's the same impulse, equal but opposite, right? So let's just consider one of them. Let's say just A, right? So I'm just going to copy below just the diagram here for A. Okay, so this is my diagram then. Now, to work out the impulse, obviously the formula is mv take away mu. Now in this case, obviously directions matter. So the impulse here is acting backwards, so we need to negate that because it's in the negative direction. So minus I is going to be mass of 1 lots of v. Now that's going to be v, but again it's in the negative direction, so minus v minus 1 lots of u, which is 4 cos 45. So if we simplify this, we're going to get minus I is minus v minus 4 cos 45. But we know what v is, right? We saw previously that v is 2.22. So I'm going to sub that in. So doing that, I'm going to get minus I to be minus 5.048. So therefore positive I, the positive impulse, is just 5.05, let's say, to 2 decimal places. And there we are, that is my impulse there. So hopefully happy with that. So you can see that most of the problem really just transforms into a standard 1D problem, which we've seen in the last chapter, right, in AS. But there we are. So we've got this worded question, right? So no diagram. So we've got a smooth sphere A of mass 2 moving with speed 6, and it collides obliquely with a smooth sphere B of mass 4. Just before the impact, B is stationary, and the velocity of A makes an angle of 60 with the lines of centres. The coefficient of restitution is 1/4, and it wants me to find the magnitude and direction of the velocities A and B after. Okay, so we're obviously going to need to draw a diagram for ourselves. So what I'm going to do again is just draw 2 fat circles like this. Okay, something a bit more circular like that. There we are. Okay, right, so let's look at A first. So it's moved, so obviously let's draw our line of centres, right? So a line in the middle like that. Okay, so initially it's moving with speed 6 at an angle of 60 to the line of centre. So it's probably going to look something like that, let's say, right? So this angle here is 60 to the line of centre. Hopefully you can see that, right? And the speed is 6. Okay, so hopefully happy with that. And so this is A and the mass is 2. And then B is stationary. Okay, so it's just staying where it is. So no speed initially. Okay, then after the collision, you can kind of imagine perhaps A would then move a bit backwards like that. Okay, And so then what about B then afterwards? Well, you might think my B might, well, probably move backwards, right? You might think it might something like this, where it's at an angle. But if it was at an angle, right, that would imply there'd be a vertical component like that. So it's perpendicular, right? But remember, perpendicular components don't change. So for example, for A, the perpendicular component, right? The perpendicular component for A is going to be 6 sine 60, right? So it will continue to have a vertical component of 6 sine 60, right? But for B, because it's not moving anywhere initially, it has no perpendicular component, which says to me that afterwards it still has to have 0 for its perpendicular component. So because there's no perpendicular or vertical component, it's just actually going to have its speed going completely horizontal along the line of centre like that. There's no perpendicular or vertical component to the line of centre. Okay, because if initially there's no perpendicular component, it will remain to have no perpendicular component. So I'm just going to call that speed W, right? Okay. So so that's the speed for B afterwards. Okay. So B, there we are. Now B has mass 4. And then for A, well, again, we've already done the perpendicular components. Now, as for the parallel part, so along the line of centres, it's going to go forwards to the right like this, and it's going to be 6 cos 60 before, and then afterwards it's going to go like that, right? So it's going to have I'm just going to call it letter V, right, for my parallel component afterwards there. Okay, hopefully happy with that diagram there. It's probably it can be a bit confusing to realize that for B, because it wasn't moving, that therefore there's no perpendicular component, so it's just going to have its speed just completely parallel, completely horizontal. But hopefully that made sense, right? Hopefully happy with the diagram here. Okay, so now again, situation is I'm just going to if I consider my parallel parts, I'm going to draw the diagram in 1D, right? So I have my spheres here, A and B. A has mass 2 and B has mass 4. So for A, well, initially it's moving to the right by 6 cos 60. And for B, it's not moving anywhere, right? So it has 0 speed. And then afterwards, okay, afterwards, A has this parallel speed of V backwards. And then for B, it has speed W forwards, right? So again, now if I just do my momentum and restitution, again, just like we did in year 1. So momentum. So for A, it's going to be mass 2, lots of the speed, 6 cos 60. And for B, it's 0, right? And then that will go to 2 lots of minus V, because it's going backwards. And then 4 lots of W for B. Hopefully happy with that, right? And so then we can simplify this to get minus 2V and 4W. We get 6, okay? Very nicely, right? We can even simplify that, and we can even simplify this even further by dividing by 2. So minus V at 2W is 3, okay? And hopefully happy with this momentum equation here, okay? Then I'm going to do restitution. So restitution, that's going to be E. Again, that's V2 take away V1 over U1 take away U2. So it's going to be W take away, then it's going to be minus V over U1 take away U2, where it's just going to be 6 cos 60 take away 0. And so that will simplify to W plus V over 3, right? And so there we are. Now, remember the coefficient restitution we're told is a quarter. So E is a quarter. Therefore, a quarter equals this expression. Okay. So very simply, we get W plus V to be 3/4. And that is my second equation there. Hopefully happy with these two, right? Again, it's just 1D collisions, right? Standard 1D collisions at this point. So I've got these simultaneous equations. W plus V is 3/4, and also 2W minus V is 3. Okay. So I can add them to get rid of the V, right? So I'm going to get 3W to be, okay, 3/4 add 3 is 15/4. Therefore, if I divide by 3, I get W to be, actually I'll do it down here. If I divide by 3, I get 5/4, okay? And there we are. That's W. Then I can find V by substituting W back into one of the equations. Let's say substitute it into here. So 2W minus V is 3. Therefore, 2 lots of 5/4 minus V is 3. And hopefully you can deduce that V then, if I solve for V, I'm going to get -1/2. Okay, and there we are. Now that's a negative result. So if I substitute these numbers in W and V, right? So W was 5/4. Now V is -1/2. Now don't freak out about the negative. Remember what the negative tells me, because it's a velocity, I'm actually going in the opposite direction. So I need to flip things, right? And then it'd be +1/2. Okay. So that's telling me actually A is going to be moving forward. Okay. So I need to flip the direction. And then V would be +1/2. Okay. And so then to adjust for the overall velocity then, well, it's going to then sort of go the opposite way like that. Okay. So if I get rid of that then, we'll be going forward here by 1/2 and then upwards by the same 6 sine 60, right? And so there we are. Okay. So hopefully happy with that, right? So if you get any negatives, again, you can just reverse the direction. Don't freak out about any negatives for the velocities. Just reverse it, right? But there we are. So hopefully happy with that. And then for B, well, we know that W is 5/4. Okay. So 5/4. Okay. For my speed there. Right. Hopefully happy with that. So now to find the magnitude and the direction of the velocities. So it wants the sort of speeds, right? Which is the magnitude of velocity. So obviously for A first. Okay. Now obviously, hopefully you can see I've got this triangle here. So if I want to find the hypotenuse, well, this side is 1/2 and this side is 6 sine 60. Therefore, the speed or the magnitude of this is going to be 1/2 squared and 6 sine 60 squared. So I'm going to do it down here. So therefore, speed of A after is going to be the root of 1/2 squared and then at 6 sine 60 squared, I believe. Yep. And so I'll square that, and then I'll square all of that and then root it if I do that. That will get me 27.25 meters per second. Okay, that's also my magnitude. Okay, for the velocity or the speed there. Okay, hopefully happy with that. I can also then do the so when it's asking for direction, again, it's basically referring to the angle. Specifically, the angle we're interested in is going to be this angle here. So you can see it's the angle between the line of center and the trajectory, right? The direction of the velocity vector. I'm going to call that angle alpha, right? So we draw our angles by the line of center. So this angle will tell me the direction of motion. Okay. So actually, again, we can do a bit of trigonometry, right? A bit of SOHCAHTOA to work that out. So it's going to be this angle alpha here. So I can also work out theta by doing tan alpha, sorry. Well, remember, tan is opposite over adjacent. So it's going to be the opposite, which is 6 sine 60, over the adjacent, which is 0.5 or half, right? And so we can just put that in the calculator and we get 6√3. So therefore, alpha is going to be inverse tan of that. And so we get alpha to be 84.5 degrees to 1 decimal place. And there we are, that is my angle, okay? So what I can say for the direction is the direction of motion, or the direction is 84.5 degrees, not percentage, degrees to the line of center, okay? And that's what I can say for my direction there. Hopefully happy with that. I can now do the exact same thing for B, and actually B is going to be really straightforward, because for B it's just like this. It's just a singular speed. I can probably just do it here actually. So then the speed of B afterwards is just going to be 5 over 4. There's no Pythagoras because it's just one length. And then as for the direction, well, it's just moving along the line of centers, okay? And direction of B is moving along the line of center, okay? Or you could say parallel to the line of center. But there we are. Okay, because the angle would effectively be like 0, right? So it's just on the line of center. But there we are, okay? There we are. Okay, so I want to go over a question where the line of centers is going to be vertical instead of horizontal. So it's going to look like this, right? So you can see the line of centers in the middle is vertical now. So I want to look at how you can deal with that sort of thing, right? So you can actually just proceed by doing the components, and you can solve it as it is vertically. So for example, if the angle here is alpha and the length is √5, this part is going to be √5 sine alpha, and then this part's going to be √5 cos alpha. Now this part is going to be perpendicular to the line of center, right? Because you got a right angle there, and this cos alpha part's going to be parallel or along the line of center, right? You can split up the components, and that's perfectly fine. You can then solve it like that. I think it's really nice if you solve everything in the same sort of way. So what you can do instead of just doing it vertically, you can kind of imagine you rotate it, or you can visualize what it will look like horizontally. You can convert it into horizontal instead, okay? So again, I've got my two spheres A and B. So this is now horizontally. So my line of centers is here. So I'm literally just going to sort of convert and switch it from vertical to horizontal. Now, if you can visualize then, so it's going to look like that vertically. Hopefully you can see then, we can say it's going to alternatively approach like that at an angle alpha with speed √5, okay? Hopefully happy with that. Likewise for B, it approaches it like that. So hopefully you can see, imagine if you tilt your head a little bit. If you tilt your head, hopefully you can see it's going to then approach the line of centers horizontally like that, okay? And at an angle beta here. And that is going to be √13. Okay? And so there we are. So you can just draw it horizontally instead, and then you can do the exact same techniques we've been doing so far. So hopefully happy with that. Okay, hopefully you can visualize how you can get this horizontally like this. Okay. Now we can do the components, right? Firstly, afterwards, let's say A rebounds like that. Okay, afterwards. And B is going to rebound like that, let's say, right? And so if I now do my components, so for A, perpendicular wise, it's going to go up like that. That's going to be root 5 sine alpha. And then we're going to go to the right, like that, parallel. So that's going to be root 5 cos alpha. Okay, hopefully happy with that. Then afterwards, again, it's going to go up like that. So that is again going to match that's going to match the perpendicular part before. So that's going to be root 5 sine alpha. Like that. And then afterwards, parallel, horizontally, it's going to go to the left like that to match the direction. And so that I'm going to call a letter V, right? I'm not going to say V cos alpha, no angle. I'm just going to call it a letter V for that parallel part. Okay, so that's A. And so then for B, originally, you can see we're going to go down here. And so that perpendicular part's going to be root 13 sine beta. Okay, hopefully happy with that. And so likewise, the parallel part up here is going to go to the left to match that direction, right? That speed there. And so we're going to go to the left by root 13 cos beta. Then afterwards, you can see we're going to continue to go down and it's going to match the original perpendicular part of root 13 sine beta again. And then afterwards, again, it's going to also move horizontally, parallel wise to the right, again, to match that direction to the right. I'm going to call that part W, right? And so there we are. Now, before we proceed, actually, we can actually simplify things because whilst I'm not given alpha or beta directly, I know what tan of those are. Now, remember, a very common technique that you really should be doing, that hopefully you've seen many times before, is if we have tan, we can find sine and cos by doing little triangles, right? So, firstly, we know that tan alpha is a half. Now, ultimately, I just want sine and cos of alpha. So, I can do a little triangle, okay? So, hopefully, again, you're familiar with this, but here we are. So, the angle alpha here. Now, remember, due to SOHCAHTOA, tan is opposite over adjacent. So, the opposite length must be 1 and the adjacent must be 2. So, the hypotenuse is going to be root 5. Okay, because 2 squared and 1 squared is 5, then you root it. Therefore, we can obtain sine alpha, which is opposite over hypotenuse, so 1 over root 5. And cos alpha is going to be adjacent over hypotenuse. And there we are, we've got sine and cos alpha like that. Also, we know what tan beta is. Tan beta is 3 over 2. So again, the same sort of technique. We do a little triangle for beta. So again, the opposite must be 3 and the adjacent must be 2. So the 3 squared and 2 squared is going to be 13. So it's root 13 for the hypotenuse. Therefore, sine beta, opposite over hypotenuse, like that. And cos beta is adjacent over hypotenuse, like that. And so I can quickly get my cos and sines, okay? And so with that in mind, I can simplify my components because my components have sine and cos, right? So here, firstly, root 5 sine alpha is 1 over root 5. So here, root 5 times 1 over root 5, that's just going to go to 1, right? So I can convert that perpendicular part to 1. Likewise here is going to be 1 there as well. Also here, root 5 cos alpha is 2 over root 5. So this part is root 5 times 2 over root 5, which is just going to go to 2. So I can simplify that part quite nicely to 2. I can do the same here for B. So cos beta is 2 over root 13. So I have root 13 times 2 over root 13 for cos beta. So that will just go to 2, that part, right? Likewise, sine beta is 3 over root 13. So root 13 sine beta is going to be root 13 times 3 over root 13. So that'll go to just 3. Okay, that perpendicular part there. As will this part. And so quite nicely, we have simplified all my components like that. Okay, so there we are. Right, now we've got that out of the way, we've got our simplified components. Again, hopefully you're happy at this point. I can now just look at my parallel parts and convert it into 1D. So I've got my two spheres, right, A and B. A has mass 2, B has mass 1. Now for A, originally it's moving to the right like that with speed 2. That's the parallel part before. For B, it's originally moving to the left here by 2. And then afterwards, A's moving to the left here. Okay, parallel right by V. To the left by V here. And B is moving afterwards to the right by W like that. And those are all my parallel parts. And so it just becomes a very standard 1D situation, which we looked at in year 1. Okay. So firstly, we're going to apply momentum, then restitution. So momentum firstly for this. So for A, it's mass 2, lots of D, speed 2. And then for B, it's mass 1, lots of minus 2 because it's going in the negative direction. Then it's going to be 2 lots of minus V. Again, it's going backwards, negative. And then 1 lots of W. So this will simplify to minus 2V and W to be 2, right? 4 minus 2 is 2. So get this equation here. Then restitution. So that's going to be E, which is V2 take away V1 over U1 take away U2. Well, in this case, we're going to put V2 take away V1 is going to be W take away V. But V is in the negative direction, so it's going to be minus V instead, like that. Then U1 take away U2. So it's going to be 2 take away 2, but this 2 here is again going backwards. So we need to negate that. So it's going to be 2 minus 2 like that. Hopefully happy with that. So that's going to be W plus V over 4. Okay. Again, pay attention to your negative directions. We must negate things if they're in the negative direction, going backwards. Right, so there we are. And also we are told what E is. E is a half, the coefficient restitution. So that's equal to a half. So therefore, we're going to get W plus V to be 2 if we multiply by 4. And there we are, we get this second equation here. So now we've got simultaneous equations. So W plus V is 2. And also for momentum, W minus 2V is 2 as well. Okay, so at this point I've got standard, quite nice simultaneous equations, so solve them however you like. I think the best way is to take these away because then the W's cancel. So you're going to get 3V is going to be 0, and therefore V is also 0. Now that's fine, I've not messed up anywhere. You can get 0, it just tells me that parallel part goes to 0, okay, that part of the velocity. And so then to find W, I'm going to sub that back, I'm going to sub this V into one of the equations. Let's say substitute it into the top one. So W plus V is 2. Therefore, you're going to get W plus 0 is 2. So therefore, W is 2. And so I've got my two solutions there, okay. So if I go back to my diagram, so V is 0, so it's going to go to 0 there, and W is 2, so it's going to go to 2 there. Okay, so now it wants me to find the speed of each sphere, so we're pretty much done, right? So to find speed afterwards, well, it's sort of, again, it's like the, so we've got the overall velocity, we find the speed by doing the Pythagoras, right? So for A, well, A is quite nice because what we've got, afterwards, right? Again, if we split it up to components afterwards, we're going up by 1 and, well, and then across by 0. But because that part is 0, that doesn't that has nothing there. Literally, the only component is 1. So that's the overall speed in that case, quite nicely. So the speed of A afterwards is just 1 meters per second, okay? I don't need to do any Pythagoras, nothing fancy. I can immediately spot that overall the speed has to be 1 there, because the other component went to 0, okay? Then for B, okay, so afterwards, okay, so I've got these two components afterwards. Okay, so I'm going to need to do sort of the Pythagoras between these two to get the overall speed. Again, we get this sort of triangle, right? So this is my speed overall. So 2 across, then 3 down. Hopefully you're happy with this triangle. So therefore you can see that the speed if I look at this triangle here, it's just going to be the Pythagoras of the two components. So 2 squared and 3 squared rooted. And so that will get you root 13. And there we are. So that's the speed of B afterwards. And there we are. So there we are. So if we want to work out speed, we can just do the Pythagoras of the components, right? So there we are. Right, so here now I've got this exam question. I'm not going to read through the text because I'm pretty much giving all the information here, okay? But what I am going to do is just redraw the diagram, right, but a bit bigger. So if I do my diagram here, okay. So firstly, again, if I draw my line of centers right for the middle. Now, okay, so now, well, before the collisions, so for A, firstly, it's going to move like that. So it's going to attack the line of centers like that with speed 3u and an angle of 30. Hopefully happy with that. So this is A. The mass is 3m, I believe. Yep. And then afterwards, it's going to look at something like that, right? So it's going to rebound like that. Okay, then for B, well, before the collision, it's going to look like that. So it's going to attack the line of centers like that with speed 2u and an angle of 30. Then after the collision, it's going to rebound like that. And we're also given an angle quite nicely of 60. Now, because we have the angle here, we can actually find the components afterwards for B without having to just solve in the normal way. So if I just focus on B first, the mass is 4, okay? So if I focus on B first, so I want to split the components. Now, perpendicular, it's going to look like that before. That's going to be 2u sine 30. And then parallel like that of 2u cos 30. Now, after the collision, what I'm going to do now is, because we have the angle, I'm going to also call the final speed here v, okay? Because now I've got my angle, I can work out what v is straight away, the overall speed. So again, if I was to again do it perpendicular, it's going to, the perpendicular component again is going to match, so it's going to be 2u sine 30. But again, because we know the angle is 60, we can also split that up to be v sine 60. And so they're equal, right? They're both the exact same length. So we can say that 2u sine 30 is v sine 60. Then we can solve for v. So v is going to be 2u sine 30 over sine 60. Now that would get me v to be, if I work that out, to be 2 root 3 over 3u. Okay, and there we are. So, so I can add that on. So it's going to be 2 root 3 over 3u. And so that also means the parallel component here, well, that would be v cos 60. But of course, we know that v cos 60, we know what v is. It's 2 root 3 over 3 u, lots of cos 60. If we work that out, that simplifies to root 3 over 3 u. Okay, so actually the parallel component we can simplify to root 3 over 3 u straight off the bat. Okay, and so there we are. Okay, so if we are lucky to be given any information afterwards, so any angles or the speed, in fact, we don't really need to split the component. We don't need to solve for anything, because we can find it right off the bat. We don't need to convert into 1D first. We can just solve straight off the bat at that point. Okay, so hopefully happy with that. Now for A then, so again we're gonna find the components for A. So vertically or perpendicular, that's going to be 3u sine 30. Hopefully happy with that. Then we're going to go parallel forwards of 3u cos 30. Then afterwards, again, we're going to go straight up like that. That's also going to be 3u sine 30. And then we're going to go parallel to the left. Now, I am going to just call that a letter W, let's say. Now, I am not going to find the components here, because I can't, because I don't know what this angle is, and I don't know the angle afterwards, and I don't know the speed. So at that point, I am just going to have to use the normal method of just calling the parallel part some letter W. And so because we don't know what W is, I am going to have to do my my 1D collision diagram to work out the parallel speed. So, okay, so if I now consider the parallel parts to find W, which is the parallel part for A, so if I draw the diagrams, so A has mass 3m, B has mass 4m. Now, the parallel speeds for A, we have 3u cos 30 there before. Then afterwards for A, the parallel part is going to be this W going backwards to the left. Then for B, well, before it's moving with 2u cos 30 to the left, parallel. Then afterwards, as we just worked out, because we've got the information with the angles and such, we could tell it's going to move forwards in the parallel direction of root 3 over 3u. Okay. And so there we are. And so then I can do momentum. So that's going to be 3m lots of 3u cos 30. And then 4m lots of minus 2u cos 30, because it's going in the negative direction. That's going to be 3m lots of w, and then no, minus w, sorry, because that's again going in the negative direction, and then 4m lots of root 3 over 3u. So hopefully happy with that. Now I can simplify all of this. So firstly, 3 times 3 times cos 30, that's going to be 9 root 3 over 2 mu. Okay, then for that part, 4 times minus 2 times cos 30, that's going to get me the numerical coefficient of minus 4 root 3 lots of mu. So then that's going to equal minus 3mw, add 4 root 3 over 3 mu. And so then, well, hopefully you can notice I can cancel the m's, because m's in every term. So therefore minus 3w add 4 root 3 over 3u is going to be 9 root 3 over 2u minus 4 root 3u. So hopefully happy with that algebra there. And actually, you can then I can move that 4 root 3 over 3u to the other side. So minus 3w is going to be minus 4 root 3 over 3u plus 9 root 3 over 2u minus 4 root 3u. And so we can collect all the u terms here to simplify. And so we get minus 5 root 3 over 6u. Therefore, we can divide by minus 3 to get w to be just 5 root 3 over 18 lots of u. And so that's my component there. Now, I don't need to do restitution because that's the only unknown here, okay, w. So that's really it. So I can add w onto my diagram. So it's going to be 5 root 3 over 18. Lots of u there. Okay, so hopefully happy with that then. Now, where do I go from here? What do I need to do? Firstly, the question is asking me to find the size of the angle through which the direction of motion of A is turned as a result of the collision. That is referring to the angle deflection, the angle through which I turn, right? Now, to do that, and again, always my strategy with angle deflections is, okay, so I'm going to draw the diagram for A out, because that's what it wants me to consider, just A. So if I draw it here then, to really help show you where the angle deflection is. So I want to draw my two velocities, right, before and after. So this is before. So again, it's going to look like that. Well, I can just use the diagram here, right? So it's going to look like this before at an angle 30. Then afterwards, like that, right? Now, the angle deflection is not going to be that angle there. Not going to be that angle. It's actually going to be to help you help see it extend the original vector like that. Okay, the original velocity. This is the angle deflection. Hopefully you can see now that's clearly going to be the angle through which I turn my velocities. Okay, so that is my angle deflection. I'm going to call that theta. Okay, how on earth am I going to work out theta? Well, actually, I also know this angle here, right? This, if I call this alpha, well, actually, this is alpha, right? It's just the angle in this triangle with these two components I've found, right? And so I can use my usual SOHCAHTOA. I can find tan of alpha by these two components, my parallel and perpendicular components, right? With this little triangle I've got. So hang on a minute, I can work out alpha. Okay, I can do SOHCAHTOA to my components I've just found out. This angle's 30. Well, hang on, look at this. Isn't this whole, in fact I'll do it in a different colour actually. Isn't this whole angle here that encompasses theta, alpha and 30, isn't that just all on the same line? That all of it has to add up to 180. And so that's how I can find the angle deflection theta. Okay, so again, make sure you extend your vector like that, your velocity like that, because that'll help you clearly see. Okay, so hopefully you can see then that these three angles have to add up 180. So theta, add alpha, add 30 has to be 180. Therefore, theta, my angle deflection, is going to be 150 take away alpha. Now, as I just discussed, we can work out alpha with this little triangle we've got here. So I'm going to draw that triangle out, my velocity triangle, if you will. So for A, This is alpha. Now, the horizontal component we just worked out, right? You can see here, it's going to be 5 root 3 over 18u. Okay, that's my parallel and my horizontal part. Then the vertical part, again, you can see in the diagram, is going to be 3u sine 30. Okay, hopefully you're with me here. So how can I work out alpha? Well, I can work out tan alpha, right? And then do inverse tan. Now tan, remember, is opposite over adjacent. So the opposite is 3u sine 30 over the adjacent of 5 root 3 over 18u. Now I'm going to simplify this. Well, the u's cancel. That is great because now we've got a number, so we can find the angle. If I simplify this, I get 9 root 3 over 5. Okay. So therefore alpha is inverse tan of that. And so I get 72.216 blah 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 degrees. So there we are. So therefore theta then can be 150 take away this 72.216 I found. And so I get 77.78 degrees to 2 decimal places, and there we are. That is my angle deflection theta. Okay, for A there. Now I'm going to be looking at more angle deflection questions later on in the video, so you get more practice there. But hopefully that made some sort of sense. Okay. Now part 2 actually, part 2 is actually fairly it's more straightforward. It's just asking for the impulse. And so if you were put off by part 1, please don't skip the other parts of the question. The second part of the question is much nicer, because how do we find impulse? Well, we just resort to my 1D diagram. So A, the impulse is here, and B, the impulse is here. Okay, so if I just consider B, then I can find the impulse by just isolating the diagram for B. So I'm just going to redraw the diagram here below. Okay, so I've just copied the diagram for B here, so I can work out the impulse then. Again, impulse is mv take away mu. So impulse here, well, it's going to be the mass, which is 4m lots of v. So it's going to be root 3 over 3u. Take away 4m for the mass, lots of u. Now it's 2u cos 30, but again, directions matter, but so we're going to negate that because it's in the negative direction. Okay. And so simplifying this then, well, I can actually pull out a 4mu out of both terms. So I'm going to get root 3 over 3, and then plus, because it's a double negative, 2 cos 30, right? Hopefully happy that factorisation there. So if I now work this out and simplify it, I get 16 root 3 over 3 mu. And there we are. That is my impulse then in terms of m and u, which is what they wanted. Okay. Okay, now we're going to be involving vectors, right? And actually with vectors, with collisions with two spheres, it's really nice because we can literally just use equations and it works out quite nicely. I don't even need to draw a diagram when we got vectors, really, because I can just use equations in a straightforward way. So let's have a look at this question here. Right, so the first thing I'm going to note down are just all the velocities, okay? So I'm going to call you A like that, okay? That's going to be the initial velocity of the first particle A, which is 2i and 3j, or as a column vector 2, 3. Okay, hopefully happy with that. Then likewise, UB, so the initial velocity for B, I'm told, is 4i minus 2j. So there we are. Now, I'm also going to write down the velocities afterwards. So VA, Well, I'm not told either of them. That's what I want to work out, the velocities afterwards. So I'm just going to call VA the vector AB, and then VB, I'm going to call the vector CD, okay? So obviously the whole idea is I want to work out what these missing coefficients are. Hopefully happy with that, okay? Right, so the main thing to pay attention to here is that I'm told the line of centres is parallel to J. So the parallel direction is the J components, right? So these components here for my vectors, right? My J parts. So we want to consider the J components. So the parallel parts are my J components. Okay, so I'm going to apply restitution and momentum to the J components. Now before I do that, because the J components are parallel, because again we just told this, right, that means the I components don't change as a result of that, right? Which means if initially the I component is 2, then actually we know that afterwards it's still going to be 2 as well. So we can fill that in straight away. Likewise for B, initially the I component is 4. And again, the I components won't change. So in this case, we can swap C for 4 as well. Okay. So immediately I can deduce that the I components remain the same, right? Hopefully happy with that. So it just remains to find B and D. Okay. B and D. And so I'm going to now look at my J components. Okay. So again, if I now firstly apply momentum, and this is again just for the J components. Now, for A, the mass is 5. So it's going to be mass times the velocity, right? So it's going to be mass of 5. Now, the initial velocity, the J component is 3. So it's going to be, so I'm going to multiply by 3 here. Hopefully happy with that. Then for B, the mass is 3. So then I'm going to add on 3 lots of the speed, which the J component is -2. Okay. Then afterwards, okay, for A, where it's going to be mass of 5, lots of the J component B. Then for B, it's going to be mass of 3, lots of the J component D. Okay. And so I get this equation here. So if I simplify it, I get 5B add 3D to B, 15 minus 6, which is 9. Okay, hopefully happy with that. Okay, so I'm just doing momentum to the J parts. Then restitution. So for restitution, we say that E is V2 take away V1 over U1 take away U2. That's how I usually work at restitution. Well, in this case, I've labelled my vectors slightly differently. So VB is going to be V2, okay. And V1 is going to be VA, U1 is going to be UA, and U2 is going to be UB. So I'm just going to plug in the J components for all these vectors, right, into this formula here. So for VB, firstly, where the J component is D, so it's going to be D, take away the J component for VA. So for VA, that's going to be B. Then I'm going to do the J components for UA, take away UB. Now for UA, the J component's 3, and for UB, it's -2. So it's going to be 3 take away -2, right? And there we are. This simplifies to D minus B over 5. Okay, because I've got a double negative on the bottom there. And so that equals E, right? So E, I'm told, is 3 over 5, right? That's my coefficient restitution. So therefore 3/5 is going to be D minus B over 5. So at that point then, I get D minus B is 3. And that is my second equation there. And so it just boils down again to simultaneous equations. So I have D minus B is 3. And I also have that that 5B at 3D is 9. and so I'll solve them simultaneously. Well, it probably helped to, let's say, triple the first equation. So I'm going to get 3d minus 3b is 9. And then if I restate the second equation, what I can then do is subtract them, right, to get rid of the 3d. And so I'm left with minus 8b is going to be 0, and therefore b is 0. Okay, so hopefully happy with that. So then to find d, I'm going to sub b back into one of the equations. Let's say I sub it into the first one here. Therefore, d take away 0 is 3. Therefore, d is 3. So those are my missing coefficients, right? And there we are. I'm done. So that means then that VA, the velocity for A afterwards, so the velocity of A is 2b. But we just saw that B was 0, so it's just 2, 0. And VB, the velocity for B afterwards, it's going to be 4d, right? But we saw that d is 3. So 4, 3 is my vector there. And there we are. There we are. So that's generally the process, right? So I want to look for the component that we parallel to, and then I just apply my standard momentum and restitution equations to that particular part. Okay, but there we are. Okay, so we've got this exam question here. Now I'm not going to read out the whole questionnaire. I'm just going to pick out the details that we need as we progress through the question, right? So firstly, it's asking me to find the velocity afterwards. So to do that, I'm just going to again do the standard techniques. So ultimately, I want to use restitution and momentum parallel wise. But let's just jot down my vectors, right? My velocities. So initially for A, I'm told before the collision, the velocity of A is 3i2j, so 3, 2 here. Then UB is going to be minus 4i minus j, so it could be minus 4, minus 1 there. Okay. And so afterwards, VA then, the velocity for A afterwards, I'm just going to call AB. But actually, we're told everything's parallel to I, right? So the J components aren't going to change. So it's still going to be 2 for J here, okay? So I can immediately add that on. Likewise, for VB, so it's going to be, well, minus 1, the J component's still going to be minus 1. That stays the same. Then I'm going to call the I component B, right? Hopefully happy with that. So now let's consider my I components, right? So my parallel parts, so I components. So firstly, momentum. Okay, well, for A, the mass is 0.2. So it's going to be 0.2 lots of the initial I component for A, which is 3. Okay. And then for B, the mass the mass is 0.4. Okay, for B. So 0.4 lots of the original I component, which is minus 4 here. Okay. So then that's going to be 0.2 for A, for the mass, and then the I component afterwards is A. And then 0.4 lots of the I component afterwards for B, which is B. Okay. And there we are. So hopefully happy with that. So I'm just applying, again, momentum to the I components for all the velocities. So if I simplify this, then I'm going to get 0.2A, add 0.4B to B. Minus 1, okay. Then restitution. Okay, so E, which again is going to be V2 take away V1 over U1 take away U2. Okay, well in this case V2, so for the I components, V2 is going to be B here, right? Then I'm going to take away V1, which is going to be this I component A, okay? And then U1 take away U2. Well, U1 is going to be 3 and U2 is going to be -4. So it's going to be 3 take away -4. So that will simplify to be minus A over 7, okay? And so E, I'm told, is 3 over 7, okay? So this is equal to 3 over 7. And quite nicely, we can times across by the 7. So B minus A is just 3. And that's my second equation there. Hopefully you're with me here. So at that point, I've got simultaneous equations. So B minus A is 3. And 0.2A, 0.4B is -1. Okay. Right, so I just solved these simultaneous equations. Now I'm going to times the bottom equation by 5 to get the A's to match. So if I times the second one by 5, I'm going to get 2B add A's -5. Okay, and so then if I bring down the other equation, B minus A is 3, then you can see I can cancel the A's by just adding them. Okay, so I'm going to get 3B is going to be -5 add 3, which is -2, right? Therefore B divided by 3, I get -2/3. Okay, and there we are. So then to find the A component, I'm going to sub B back into, let's say, the first equation. So, -2/3 for B, minus A is 3. Therefore, A, solve this equation. I get -11 over 3. And there we are. So to summarise my two velocities, VA firstly, so VA was A2 and A is -11 over 3 and then 2 there, okay, and VB VB is B -1. And so B is -2/3, okay, and there we are. Those are my two vectors, okay. Those are my two velocities afterwards. Okay, so fairly straightforward, 7 marks, I think. So that's the velocity for A, and then for part B, what's the impulse for A? Okay, so now the impulse for A, but again, the impulse is equal, so you could actually consider B if you wanted to, but let's just do it for A. So impulse, again, my standard formula is mv to equate mu. So for A, my impulse, now the mass for A was 0.2, I believe. Yep, 0.2. And then so if I pull that mass out, I'm going to get V take away U, and so that would be 0.2. So then V minus U. So what's so again, this is going to be for the I components because that's where the impulse acts parallel, and we're parallel to I. So we're just going to consider the I components. So what's the I component at the end? Okay, so for A, at the end, my I component is -11 over 13. Take away the initial I component U, which you can see here for UA is 3. Okay. So this simplifies to -4/3. Okay. Now that's the physical impulse, right? So it's negative, which means it will be acting in sort of a negative direction. But again, it's asking for the magnitude of the impulse, so we need to make it positive, right? So the magnitude is what we call mod I, the magnitude of I, and so that's just going to be the physical positive answer, which is just positive 4/3. And there we are. And so then in part C, it says to find, to the nearest degree, the size of the angle through which the direction of motion for A is deflected. So once again, it's referring to the angle deflection. And so once again, I'm going to copy out my two velocities before and after for A. So UA is 2, 3. No, sorry, UA is 3, 2. Sorry. And then VA afterwards, we worked out to be minus 11/3 and 2. So roughly, UA, okay, that's telling me I'm going to go 3 to the right and then 2 up. So that's what my initial velocity is going to look like. Then afterwards, we're going to go to the left by 11/3, something like that, right? And then upwards by 2. So that's what's going to be, that's what my vector is going to look like there, okay? So overall, that's what my trajectory is going to look like, okay? Now, of course, so to work out, to visualize where the angle deflection is, if I again was to extend my initial vector like that, you can then see this theta between these two vectors is going to be my angle deflection. So I can just use my standard formula from Corpure, which is again A dot B over mod A mod B, to work out the angle theta between these two vectors. So cos theta is going to be again 3, 2 dotted with minus 11/3, 2 over the magnitude of them, right? So if we work all this out, we're going to get 3 lots of minus 11/3, add 2 lots of 2 over root 3 squared, add 2 squared, times by root minus 11/3 squared, add 2 squared. And so this is just a job for the calculator. If we simplify this, we get cos theta to be minus 0.464, blah, blah, blah. Okay, so I'll just do inverse cos. Okay, so theta, if I do inverse cos of that, I get 117.699, blah, 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 degrees. But then to the nearest degree, to the nearest whole number, is just going to be rounded up to 118, okay, to the nearest degree. And there we are. Right, so we've got this other exam question here. Again, I'm not going to read through it, but I note, again, it's going to be another one of these sort of vector questions. I've got these velocities, and I also note that the line of centre, everything's parallel to I. So that means I'm going to do my normal method I've been doing so far. So the first thing I'm going to do, again, is note what velocities I have. So I've got these spheres P and Q, okay, so I'm going to call it UP for the initial velocity for P, and I'm told the initial velocity for P is UI and 2J, so it's going to be U and 2. And then UQ, the initial velocity for Q, I'm told is at minus 4I and 3J, okay, so minus 4, 3. And so I want to work out the velocities afterwards, right? So I want VP, and so for VP then, well, again, I'm parallel to I, so immediately the J components are going to remain the same. So it's going to be A2, okay, some number A, and then VQ is going to be B3. Hopefully you can see that, right? Again, the J parts remain the same because we're parallel to I. So because we're parallel to I, so the I components, we're going to do momentum and restitution. Okay, so firstly, momentum. Okay, so for P, the mass is 0.3. So it's going to be 0.3 lots of the initial I component, which is this U here. Oh. And then for Q, the mass is 0.5. So it's going to be 0.5. And then -4 for the I component there for Q. So then it's going to be 0.3 lots of the I component A for P afterwards, and then it's going to be 0.5 lots of B, okay, for Q afterwards. So hopefully happy with that. Hopefully happy with all those I components there. Okay, so I can simplify this to 0.3A, add 0.5B to be 0.3U minus 2. Okay. And then we got restitution. So again, E is V2 take away V1 over U1 take away U2. So here, well, for the I components, V2 and V1 are going to be B and A. So B take away A on the top. B take away A here. Then U1 take away U2. So that's going to be U for U1 and -4 for U2. So it's going to be U take away -4. So that will simplify to B minus A over U plus 4. Now I am also told again that E is 3 over 5. Okay. So 3 over 5 is equal to B minus A over U plus 4. So then if I cross multiply, I'm going to get 3 lots of U plus 4 to be 5 lots of B minus A. So if I expand this, I get 5B minus 5A is 3U plus 12. And that's my second equation there. Now, I'm not going to be able to solve these equations here because you'll notice I have a third variable U involved. So I need to actually look back at the question, but hopefully happy so far. Again, I'm just doing the standard techniques, the standard equations. Hopefully with me here. So I'm told this stuff about angle deflections. I'm told for P, the direction of motion is deflected through an angle of 90. So that's telling me my angle deflection is 90 degrees. It's perpendicular. And as we have seen, the angle deflection, okay, is going to be the angle between the two velocities. So for P, let's say UP looks like that, and then VP is going to look like that, okay? So the angle of deflection is the angle between them, but hang on, it's actually 90 degrees. So these two velocities are going to be perpendicular. Now, hopefully you remember how we can deal with two perpendicular vectors from corporeal. They're going to be perpendicular, so their dot product is going to be 0. Okay, so if I now do that, I can get a third equation. So UP, okay, so remember I've got these two expressions for UP and VP. So U2 for UP dotted with A2 for VP equals 0. So if we do that dot product, we're going to get UA plus 4 equals 0. Therefore, UA is minus 4. Okay, which really looks quite nasty, right? It's not a nice equation, really. But that's the equation here, nonetheless. So UA is minus 4. So we've got these three equations, right? We've got UA is minus 4. We also have these two equations, right? So we also have that 5B minus 5A is 3U add 12. And we also have that 0.3a and 0.5b is 0.3u minus 2. Okay. Right, so we've got these three equations, right? And we've got three variables, so we have simultaneous equations, right? Not the nicest looking equations, but we can try and solve them. Now, I think it's probably best to probably rearrange A and B into U. And so I can substitute it into this formula to find U, which is what the question wants. So I'm just going to rearrange these two sort of nice linear ones into U. So it's just going to be algebra from here. So firstly, I can see that 5b is going to be 5a, add 3u are 12. Therefore, b is going to be a fifth of this. So it's going to be a add 3 over 5, u add 12 over 5. Okay. And so I'm going to sub that into the next equation here. So 0.3a add 0.5 lots of a add 3 over 2, add 3 over 5, sorry. U add 12 over 5 is 0.3u minus 2. So if I expand all of this, I get 0.3a add 0.5a add then 0.5 lots of 3 over 5 is 3 over 10 lots of u add 0.5 lots of 12 over 5 gets me 6 over 5 equals 0.3u minus 2. And so I can now rearrange for A in terms of the subject. So I'm going to get 0.8a on its own. If I now move everything else to the other side, I get 0.8a. And actually the u's cancel very nicely. 3 over 10u, well, that's 0.3u. 0.3u cancels with the 0.3u there. So actually it simplifies very nicely. So 0.8a just goes to minus 2. So the u's cancel. So we get minus 2 minus 6 over 5 is just minus 16 over 5. So a then divided by 0.8, I get minus 4. So actually the equations look scary, but once you do the algebra, solve them manually, it works out very nicely. So a is minus 4. So so now I can work out what u is and can sub a into here. So u lots of a, which is minus 4, is minus 4. Therefore u is going to just be 1. Okay. And then I can find b. Okay, so b is going to be a, which is minus 4, plus 3 over 5 lots of u, which is 1, add 12 over 5. So get b to be minus 1. And there we are. So I found u, b and a. So now I've found all my missing values, I'm just going to restate my velocities, right? So UP was U2, remember, but U is 1. So I can say it's 1, 2. UQ was minus 4, 3. That we were given, right? Then VP was A2, but A is minus 4, so minus 4, 2. And then VQ was B3, okay, B3. So that's going to be minus 1 for B and then 3. So that's where we're at. So hopefully you're happy with that. Okay, and then part B is asking to find the value of alpha. Now, alpha, as you can see here, is the angle deflection for Q. Okay. Now, again, I've already went over that in the previous few questions. Now, the angle of deflection is just going to be the angle between the two velocity vectors. So for Q, it's going to be UQ and VQ, right? So the angle deflection for Q Well, that's going to be cos theta, right? And so that's going to be the two velocity vectors minus 4, 3 dotted with minus 1, 3 over their magnitudes, right? So simplifying this, we're going to get minus 4 lots of minus 1, add 3 lots of 3, all over the root of minus 4 squared, add 3 squared, times by minus 1 squared, add 3 squared. And so at that point, we can simplify it to get uh, 13 root 10 over 50. So that's cos theta. So we just inverse cos that. And so we get 34.695 blah 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 degrees. They don't tell me what to round it to, so I'm just going to round it to, let's say, 1 decimal place, right? So 34.7 degrees to 1 decimal place. So that's going to be alpha, sorry. That's alpha specifically, okay? That's my angle there. So there we are. Okay, now part C is asking, state how you use the fact that P and Q have equal radii. Now, I must admit, I was stumped by this particular part of the question. So shout out to R2 Drew 2. When I looked at this in more detail, I think his explanation made sense. Right, so far, we've only really been working with circles. Right, so all our collisions, all our problems look like this, right? Where two of the objects, right, they collide like this, okay? So we just got two circles like this. Now, in reality, we're dealing with spheres, okay, which are 3D objects. We're looking at it through circles, which is 2D, but actually the spheres are 3D. So how does that work? Well, what we've been doing actually is we've been looking at these situations, so the physical situation of these two spheres colliding. We've been looking at it in a particular way, okay? And what I mean by that is we have been looking at the two spheres as a plan view, okay? Which so a bird's eye view. So imagine we're looking down onto it, okay? So you might be so again, remember from GCSE, you should have looked at plans, front views and side views and elevations, stuff like that. So we've been looking at it through the plan view from the top down like that, okay? And so when we look at the two spheres like this from the bird's eye view, it does look like just two circles like we've been doing so far. But when we, let's say, change our perspective and look from the front, okay, looking at the front of the spheres, and so actually this whole time with all the problems we've looked at, the two spheres have always been on the surface, okay? They've always been rolling on a sort of surface or ground like this, okay? It's just that when we look at it through a bird's eye view, we don't see the surface because it's just completely flat. So we ignore that, right? But they're technically on a surface, right? So you can see when we change the sort of the viewpoint, we get a different picture of the same situation, okay? Now, what that means is, as you can see here, the line of centres is sloped, but the surface isn't. That causes an issue, okay? What we actually want is, we want the surface the spheres are on to be parallel to the line of centres. That is because when the surface is parallel to the line of centres, okay, that then allows us to do the methods we've been doing so far. So we can just convert it into 1D, only consider the parallel parts, because when a surface is parallel to the line of centers, that ensures that only the parallel parts of the speeds change, okay? So it allows us to do the methods we've been doing so far, okay? Now, that's always happened, okay, because the two spheres have the same radius, okay? But as you can see here, the two spheres have different radii, right? One's clearly got bigger radius than the other. That causes the line of centers to become sloped and disjoint, okay, like that, okay? If the two spheres were to be equal radii, like that, then you can see the line of centers will then be parallel and match the surface like that, okay? And so that's the underlying assumption we've been using, okay? So therefore, because the two spheres have equal radii, the line of centers, the line of center is parallel to the surface they're on. Because if they weren't the same radius, then the line of, that would force the line of centers to be sort of sloped like that, okay? That's not what we want. We want it to be matching the surface. Anyway, so it's parallel to the surface. What that means as a result is, as I've discussed, that the parallel parts change and the perpendicular parts don't. More specifically, it's the impulse that remains parallel. And so because the impulse remains parallel, impulse actually affects the speed, right? It's the impulse that changes the speed, technically. So so basically the spheres have equal radii, the line of centers is parallel to the surface. So if it's parallel, that means impulse is parallel, which therefore means the speeds change parallel, and so that allows us to do the methods we've been doing so far. Again, very awkward 1 marker, but if it ever comes up, this is the sentence you kind of want to write to get that mark, okay? That in brackets there. But very awkward question, but there we are. Now we're going to be looking at vectors, but now the line of center is sloped. So in other words, it's not going to be parallel to I or J. So you would have noticed with the previous few questions we looked at, it was either parallel to I or J. So the line of centers would look horizontal, which would be I, or completely vertical, which would be J, okay? And so that allowed us to nicely just work with the I or the J components and then use restitution and momentum on those particular components. But when it becomes sloped, so it's going to be at an angle like that, it complicates things because we can't just look at one of the components of the vectors, okay? Because what would happen is that a velocity, right, would both its components would have parallel and perpendicular parts. So we're going to have to involve both the components, the I and J parts, for all the velocity vectors, okay? So it overcomplicates things a little bit, but the main essence is we still are just going to use equations, right? So we're going to be using momentum and restitution, but the equations are going to be a bit different. So I want to talk about restitution. So again, there's a nice little formula we can use to work out restitution in this case, okay? And you can see it's pretty analogous to the standard restitution formula, which is just V2 take away V1 over U1 take away U2, okay? So there we are. So basically this sort of formula for E basically encompasses this definition for E and the vector formula we saw with the wall, right? So I believe it was V dot I was minus EU dot I. If we rearrange that, we're going to get E to be minus V dot I over U dot I. Okay, and actually, because it's because we have a minus on the front, we can just put a modulus around it, and then we could just make it positive because E has to be positive, right? So there we are. So we got to this formula for E, right? Okay, when we looked at in the previous video, where we looked at collisions with walls, but hopefully you can see now that the V and the U part, right, changed to V2 take away V1 and U1 take away U2, which is where it combines the standard formula, right? So there we are. So that's how we arrive at this sort of formula for E. Okay, so we just basically just combine the standard restitution equation and the equation we looked at with walls, right? So there we are. So let's just jump into this question then. So obviously if we want the speed, we're going to need to find the velocity, right? So again, the process is going to be the same. I'm going to want to note what my velocities are. So UA firstly. So the initial velocity of A is 3I minus 5J, so 3 minus 5. UB, my initial velocity for B is 4I and J, so 4, 1. VA, okay, we're actually given VA, it's 4I minus 4J, so 4 minus 4. And we want to work out the velocity of B, okay, because then we can do Pythagoras magnitude to work out the speed. So I'm just going to call that AB, okay. So it's not parallel to I or J, okay, the line of centers, right? They don't tell me, okay, so that's one dead giveaway. If they don't tell you it's parallel to I or parallel to J, that's one giveaway that you can't just use what we did before, okay. The other giveaway is, because we're given the before and after velocity for A, if it was parallel to I and J, or I or J, one of the components must remain the same, right? Because if it would be parallel to only one of the components. But actually notice for A, originally I is 3, then it changes to 4. So I doesn't stay the same. But for J, it's minus 5, and then it turns to minus 4. So J doesn't remain the same either. So that tells me the line of centers must be sloped. Okay, so it's not going to be horizontal, vertical, or I or J. Okay, so all the components are changing. So I'm still going to do momentum. Okay, so I can't do anything else. So I'm going to do momentum. And now, because as I said, all the components are changing here, I'm going to apply momentum to all the vectors as a whole. Okay, so firstly for A, the mass is 3m. So it's going to be 3m lots of the velocity UA, okay, which is 3 minus 5. So I'm just going to use the whole velocity, right? Then for B, the mass is m, so it's going to be m lots of UB, which is 4, 1, right? And then that's going to equal afterwards 3m for the mass, and then VA, which is 4 minus 4, and then m lots of VB, which is AB, okay? And actually, before we even start simplifying and or adding the vectors together, we can just get rid of the m's, okay? Because we can divide through by that. So we're going to get 3 lots of 3 minus 5, add 4, 1. It's going to be 3 lots of 4 minus 4, and then AB. Then we can start combining vectors. So we're going to get 9 minus 15 if we multiply the first vector by 3, and then 4, 1 equals 12, and then minus 12, add AB. Then let's combine the vectors together. So on the left side, 9 add 4 is 13, minus 15 add 1 is minus 14, equals 12 add A, and then minus 12 plus B. And then you can see how I'm going to get A and B by just comparing the coefficients. So 13 is 12 add A, Therefore, A is 1. Likewise, minus 14 is minus 12 at B. Therefore, B is going to be minus 2. And so those are my components. So the velocity of B afterwards, VB, which is AB, which is 1 minus 2. And there we are. So it's asking again for the speed of B. So remember, speed is going to be the magnitude or the Pythagoras of the velocity. So the speed afterwards for B is going to be the magnitude of the vector 1 minus 2. And that's going to just be root 1 squared add minus 2 squared. And doing that will get me root 5. Okay. And that is my speed there. Okay. So that's the idea. So it's largely the same process. We use momentum, but we're going to apply it to the vectors as a whole. Okay. Because we can't just split things into one component. Okay. Then part B is asking for the kinetic energy lost in the collision. So again, my standard formula for loss in kinetic energy with collisions is kinetic energy before, take away kinetic energy after. So if we want to work out our kinetic energies, obviously we're going to need to find the speed. So it might be a good idea to work all that out first, right? So firstly, the speed of A before. Well, that's going to be, well, the velocity for A before is 3 minus 5. So it's going to be the Pythagoras. So root 3 squared and minus 5 squared. So that's going to be root 34. And so then the speed of B before well, again, that's going to be the magnitude of the initial vector for 1 here, okay? So it's going to be the root of 4 squared, 1 squared. So that's going to be root 17. Then the speed of A before, the speed of A afterwards then, well, it's 4 minus 4 for the vector. So Pythagoras of that is going to be 4 squared and minus 4 squared. So that's going to be 4 root 2. Okay. And then the speed of B after, well, actually, we've just worked that out, haven't we? The speed we said was root 5. Okay. So now we can work out the kinetic energy. So before the collision, for A the mass is m. No, sorry. For A the mass is 3m and B the mass is m. Okay, A is 3m and B is m. So it's going to be half lots of 3m, lots of the initial speed, which was root 34. Then we need to square that, right? Then we need to add on the kinetic energy for B, which is a half lots of the mass m, lots of the initial speed, root 17 squared. Hopefully happy with that. So if we simplify this, we get 119 over 2m for my kinetic energy before. Then afterwards, well, again, it's going to be half lots of 3m for the mass of A. Then the speed of A afterwards is 4 root 2. We need to square that. And then for B, it's half lots of m. And then it's going to be root 5 squared. Okay. And again, if we now simplify that, we get 101 over 2m there. So therefore, the overall loss in kinetic energy is going to be the kinetic energy before 119 over 2 lots of m minus 101 over 2 lots of m afterwards. And so that simplifies to 80. 9m. Okay, and so that is my expression for the loss of kinetic energy there. Okay, right, so now in part C, so I've added these two parts on, right? So in part C, I'm now looking for a unit vector parallel to the line of centres, okay? Well, again, as I discussed, the question hasn't mentioned where the line of centre is or where the parallel part is. But what do we know is parallel? The impulse, right? So we can find the impulse. Okay, so if we want to find a vector parallel, it's going to be the impulse, right? Because that's where it acts. So remember, impulse m is mv take away mu. So I'm going to need to consider either A or B. Let's consider A. So let's find the impulse for A, right? Because again, the impulse is going to be the same for both the spheres. So just consider one of them. Anyway, so for A, impulse m. Now for A, the mass is 3m, okay? So it's going to be 3m lots of v minus u. Hopefully happy with that. So now... so v minus u. Now again, I'm just going to now use the vectors, okay, as a whole, okay, because I'm not good. I can't split things up in terms of just I and j. So for A, the final vector is 4 minus 4, and then initially it's 3 minus 5. Hopefully happy with that. So I'm going to take these two away. So 4 minus 4. Take away 3 minus 5, right? So I'm going to get 3m, and then if I work out this subtraction here with the vectors, 4 minus 3 is 1, and then minus 4 minus minus 5, that'd be plus 1 as well, okay? And so I get 3m lots of 1, 1. Okay, or you could say in I and j, 3i lots of I plus j if you wanted to. Okay, so this is my impulse then, right? My impulse vector. Now, if I go back to the question, what is it asking specifically? It's asking for a unit vector that's parallel to the line of centres, okay? So what that is saying is I don't necessarily need the impulse, I just need a vector that's parallel and then find a unit vector for it, okay? Now obviously the impulse vector is parallel because that's how the impulse works here. It's always parallel to the line of centres, but I just need a vector that's parallel, okay? So I don't need the whole impulse, I can literally just take the vector part of it, and so that's also going to be parallel. It's going to be in the same direction, okay? So what I can say is so a vector that's parallel to line of centers is, I'm going to represent this by an I with an arrow on top of it. So what that is, what I'm saying there is it's a direction vector. Okay, it's a direction vector in the same direction as my impulse. It's not going to be the exact impulse vector, but it's just going to be a parallel vector. It's going to be in the same sort of direction. So I'm just going to call it I and j. Right, hopefully you're with me here, right? So I'm just physically taking the vector part of it, okay, because that's also going to be parallel in the same direction, okay? It's a direction vector, right? So this is my direction vector for the impulse, okay, in the same direction. Hopefully happy with that. Right, so there we are, but the last thing they want me to do is to find the unit vector, right? Now remember, the unit vector has magnitude 1, so we need to divide by the magnitude. So unit vector, well, before, okay, so if we work at the unit vector then, well, what's the magnitude of this? So the magnitude of this, again, it's the Pythagoras, it's going to be root 1 squared and 1 squared, right? Because if we because we have 1i and 1j, so we need to square the components, so you get 1 squared, and 1 squared could be root 2. So that's my magnitude for this vector. So the unit vector, that we just divide by that, okay? So 1 over root 2, lots of I and j, okay? And hopefully happy with that. So again, remember from normal maths, you would have seen unit vectors, okay? So you just divide by the magnitude. And that's it, okay? You could also then write that in column notation. So it'd be 1 over root 2, 1 over root 2, like that, alternatively. But there we are. So hopefully you're happy with that. Right, and now the final part of the question is now asking for the coefficient restitution between the two spheres. That's where this formula is going to come into play, okay? So I'm just going to copy it down below, right? And then we'll work with this formula. And so I've also copied down the 4 velocity vectors, right? Which again, I've literally just copied from here, right? My little list that I've done at the start, okay? So hopefully happy with that. Those are my 4 velocity vectors. So just noted them down here. And again, hopefully happy with the notation, how I've labelled the 4 velocity vectors, right? So the initial velocities for A and B, and then the final velocities for A and B, okay? Or particle 1, particle 2, whatever you want to call it. Hopefully happy with my velocity list here. Now, obviously, the last ingredient I need before I just plug things in is this I with an arrow on top. Now that represents what I just discussed previously. That is going to be the direction vector of the impulse. Okay. Now, actually, we said that that the direction vector I with an arrow, I said it's I and j or 1, 1. Okay. So I'm going to use it here, right? So what I need then is essentially just a direction vector or a vector representing the impulse, okay? So that's what I'm going to take here, okay? So I hat is 1, 1, which is a direction vector for the impulse. So I don't need so I don't need the full impulse. I also don't need a unit vector for the impulse. I just need a vector that's in the same direction, that's parallel to the impulse, okay? And so there we are. So now I'm happy and I can just plug things into the formula. Now before I do, I'm going to need to work out these two subtractions. So V2 take away V1 and U1 take away U2. So I'm going to do that here, okay? So firstly, V2 take away V1. So I'm literally just going to take away the vectors. So V2 is here. So 1 minus 2. Take away V1, which is 4 minus 4. That will get me 1 minus 4 is minus 3. Minus 2 plus 4 will be positive 2. Okay. Then if I also do U1 take away U2. Okay, so U1 is 3, 5 and U2 is 4, 1. So 3 minus 5 take away 4, 1. So 3 take away 4 is minus 1 and minus 5 minus 1 is minus 6. Okay, so that's absolutely everything. So now I'll just plug things into my my formula for E. So therefore E is going to be the magnitude of V2 take away V1 is this vector here, right? Minus 3, 2. Dotted with my direction vector for I. So it's going to be 1, 1. All over U1 take away U2. U1 take away U2 we worked out to be minus 1, minus 6. Dotted with again the I. Okay, so 1, 1. And so we just need to calculate these dot products, okay? So again, that's just back to corpuscle when we looked at vectors. So that's going to be minus 3 lots of 1 and 2 lots of 1 on the top, and then minus 1 lots of 1, minus 6 lots of 1 on the bottom. So if we work that out, we get 1 over 7. Okay, and actually that's also positive. So we can just drop the magnitude and just get positive a 7 for the coefficient restitution there. Okay. And there we are. So that's my coefficient of restitution there. Again, we're just going to be applying that formula whenever they ask for the coefficient restitution. In this case, where we don't know the line of centres, it's not I or J. So there we are. Okay, so then we've got this question here. So now, what's the key giveaway with this question that I can't just compare the I or the J components like we did in the previous section? Well, two key giveaways. The first one is they don't even tell you it's parallel to I or J, the line of centres, okay? Usually they don't tell you it's parallel to I and J. That's a giveaway that you're going to have to compare both the components. So we're going to have to use momentum on the whole vectors, okay, instead of just I or J. The second giveaway is, if I just note my velocity, so UA is 2.5, UB is 2 minus 2, and VA is 3.4. The other key giveaway that I'm going to have to consider both components, not just one of them, is that because I've got the initial and final velocity of A, look and see how none of the components are the same. For I, initially it's 2, then it goes to 3. That doesn't stay the same. Then for J, it goes to 5 and then to 4. That also doesn't stay the same. So because both components stay the same, that means the line of centres is not I or J. Okay, so we're going to have to apply momentum to the vectors as a whole. Okay, so we have to use so we're going to have to use the method we looked at in the previous question instead. So momentum then. So if I now call the velocity of B afterwards, I'm going to call that vector AB, right? So if I now apply momentum, well, for A, the mass is 2m. So it's going to be 2m lots of UA, which is 2.5. And then for B, the mass is m. So it's going to be m lots of UB. So 2 minus 2 is going to be 2m lots of VA, 3.4. And then m lots of AB. Hopefully happy with that, right? So I'm just applying momentum to the initial and to the velocity vectors as a whole. Okay. So if I simplify this, well, actually I can get rid of the m's straight away. So we get 2 lots of 2.5, add 2 minus 2 is 2 lots of 3.4, add AB. Okay. And so this will simplify to 6, 8 equals 6 add A, 8 add B. Okay, and then if I now compare the two components, I can see that 6 plus A is going to be 6, which would therefore mean A is 0, and also 8 add B equals 8, so therefore B also equals 0. So quite interesting. So that means that the velocity for B afterwards, VB, which is AB, well, they're both 0. Okay. Which basically tells me it goes to rest. Okay, so the second particle B goes to rest afterwards because there's just nothing there. Okay, and so there we are, hopefully happy with that. So I'll just apply momentum there in that case. Then for part B, it wants me to find the coefficient of restitution between the two spheres. Again, as I discussed, it's not parallel to I or J. Okay, so we're going to have to apply this formula for E here, okay, because you can't just use one of the components, so we're going to have to use the vector form for coefficient restitution. So obviously if you look at the formula then, obviously I've got my 4 velocity vectors, but I'm missing an impulse, right? So I'm going to need to find the impulse, okay, before I find E. Right, so remember impulse is mv take away mu, and again I can just consider either particle, right, because it shouldn't matter. Let me consider B, okay? Let me find the impulse for B. So that's going to be impulse is the mass m. Now for B the mass is m, Okay, so it's just literally m, lots of v take away u. So in this case, for b, well, the final velocity v is 0, 0. And the initial velocity u for b is 2 minus 2, right? So there we are. So I'm just taking away the initial and the final and initial velocity for b. Hopefully happy with that. So simplify this. I'm going to get m lots of minus 2 plus 2. Okay. So that's my impulse vector. But again, I only want a direction vector. Okay. I just want a vector for it. Okay. So the direction vector, which I'm going to represent like this. Well, we'll just set the physical vector part. So it's going to be minus 2, 2. And there we are. So hopefully happy with that. So that's my direction vector for the impulse. Right. So now I have my ingredients. So remember that E is this formula here. So it's magnitude of V2 take away V1 dotted with I over U1 take away U2 dotted with this I as well, this direction vector for I. Right, hopefully you're with me here. Now, I'm just going to sub my vectors in, okay? So, V2 take away V1, well, V2, VB is 0, right? So 0, 0, take away V1. Now, V1, which is also VA, is 3, 4. Okay, so take away 3, 4. Then I'm going to dot that with this I, which is minus 2, 2. Then I'm going to divide by U1 take away U2. So U1, remember, U1 or UA is 2, 5, and U2 is 2 minus 2. So 2, 5 take away 2 minus 2. And then I'm going to dot all of that again by the same I vector. Okay. Sorry, not a bracket, it's a modulus. My apologies. And so we just need to simplify this whole thing down at that point, right? So, simplify the top bit. 0 take away 3 is minus 3. 0 minus 4 is minus 4. And then 2 minus 2 is 0. 5 minus 2 goes to plus 7. Then if we work out the dot products, we're going to get minus 3 lots of minus 2, minus 4 lots of 2, all over 0 lots of minus 2, add 7 lots of 2. And so then that will simplify to minus a seventh. Okay. So that's E. Now, of course, this is where the modulus, right, comes into play, because we need to then flip it to a positive. So the whole idea with these sort of modulus signs is that we flip negatives to a positive, right? So therefore, E is just a positive answer. So it's just positive a seventh. Okay, and there we are. Okay, and then I've got this question here. So I'm told a red ball is stationary on a rectangular billiard ball OABC. It is then struck by a white ball of equal mass, equal radius, moving with velocity u lots of minus 2i at 8j. After the impact, the velocity of the red ball is parallel to minus I and j, and the velocity of the white ball is parallel to 2i and 4j. Prove that the coefficient restitution between the two balls is 3 over 5. So again, it's a bit of like a contextual part of the question where it's talking about billiard tables and stuff like that. Again, it's just snooker, but you don't need to worry about that. The main essence again is that we've got two balls colliding and we've got all their velocity vectors. So we're just going to focus on our usual techniques. So if I just note the velocity vectors first. I'm going to call U1. So this is going to be the initial velocity for the red ball, right? That comes first. Now I'm told originally it's stationary. So the original velocity is going to be 0, 0. Okay, hopefully with me here. Then U2 is going to be the other ball. So it's going to be the white ball. Now, originally, the white ball has velocity u, lots of minus 2i, and 8j. So I'm just going to times by the u, okay? So it's going to be minus 2u and 8u, okay? Hopefully happy so far. Right, now this is where things get a tad bit more complicated, because we're told afterwards the red ball is parallel to the vector minus I and j. The velocity is parallel to this. So what we can say is that v1 then, so the final velocity of the red ball, if it's parallel to the vector minus I and j, we can't say it's minus 1 and 1. We can't say that. It's parallel to it. They're not the same thing, remember? So if it's parallel to this vector minus 1, 1, that means it's going to be a multiple, a scalar multiple. So I'm going to call it k lots of minus 1, 1. Hopefully you're with me there. So remember, being parallel to a vector means it's a multiple of that vector. Okay, it's not the same vector, it's just a multiple. Okay, again, I'm going to bring that multiple inside, so it's going to be minus k and k, okay, for some number k. Then lastly, v2, so for the white ball afterwards, again, it's parallel to the vector 2i and 4j. So it's not going to be equal to the vector 2, 4. It's going to be, again, a multiple because it's parallel. I'm going to call that lambda, okay, to represent the multiple. Again, I'm also going to bring that in the bracket, in the vector itself. So 2 lambda, 4 lambda. Okay, and there we are. So, there we are. Hopefully happy with the idea of parallel vectors here. So these are my expressions for the velocities here. So firstly, if I apply momentum. So, firstly, the red ball... sorry, they all have equal mass, okay? So I'm just going to call the mass m, okay? They both have the same mass, they're equal. So it's going to be m lots of u1, 0, 0, add m lots of u2, which is minus 2u and 8u. That's going to be equal to m lots of minus kk, and then m lots of 2 lambda, 4 lambda. And of course, the first step we can do is just divide by the m, right? Cancel the m out. And so we get 0, 0, add minus 2u, 8u to be minus kk, and 2 lambda, 4 lambda. Okay. And so then we can deduce, if we add these together, minus 2u, 8u is going to equal 2 lambda minus k, 4 lambda add k. Okay, hopefully happy with that. That's just vector addition. And so then I can compare the I and j parts. So I can see that 2 lambda minus k is going to be minus 2u. And also 4 lambda add k is going to be 8u. Okay. So I've got these two equations. Obviously, I'm not going to be able to solve for all three of them because I've got two equations with three unknowns. I'll need another equation. There's not going to be another equation. So let's just rearrange to get all of them in terms of one of them. Okay, so let's just rearrange. So if I call this equation 1 and 2, okay, if I now focus on the first one, so rearrange the first one. So 2 lambda minus k is minus 2u. It's probably best to solve for k, right? It's pretty simple. I can just add both sides by k. So k, hopefully you can see, is going to be 2 lambda add 2u. Okay. And there we are. Hopefully you're happy with that. Then if I rearrange the second equation, so that is telling me 4 lambda add k is going to be 8u. I can immediately plug in k. So that's going to be 4 lambda add 2 lambda add 2u equals 8u. And so that means 6 lambda add 2u is 8u. Therefore 6 lambda If I take away 2u, I'll get 6u. Therefore, lambda is u. Okay. And there we are. And actually, then we can further simplify k, because we know that lambda is mu. So k is 2u add 2u, which is 4u. Okay. And so now I've got simplified expressions for k and lambda in terms of u. Okay, now again, as I said, there's no more equations I can pull out of thin air to kind of get a third equation and solve. But maybe I don't need to solve I don't need to find the actual numbers, the solutions. I just need to find the coefficient restitution. So remember, I can calculate E again with this formula here. But of course, I'm going to need an impulse. Okay. So I'm going to need to consider the impulse for either the red or the white ball. So the first or the second ball. It's probably best to consider the first one, the red ball, because I know that velocity is 0, 0. So it might just be easier to simplify. So what I'm going to do now, in order to be able to use and find E, I'm going to need to find an impulse vector. So if I consider for A, and sorry, for the first ball, the red one. So that's going to be I is mv take away mu. Well, in this case, I've just called the mass m, right? So it's v take away u. So, okay, in this case, if I look back, for the first one, the final velocity is here, minus kk, right? Then I'm going to take away u, which, as I said, the initial velocity for the first one is 0, 0. Okay. And so that goes to m lots of minus k, right? And actually, I can pull out a k. So it'd be mk lots of minus 1, 1. And now you can see the vector we're going to take, right? So my direction vector for the impulse is just minus 1, 1. Okay, hopefully you can deduce that. Right, so now I can finally apply my formula, right? So therefore E is going to be the magnitude of V2 take away V1 dotted with I all over U1 take away U2 dotted with I. Okay. So at that point then, well, if I now sub in my vectors, so firstly, V2 take away V1, so it's going to be 2 lambda, 4 lambda, take away minus kk. Okay. It's going to be 2 lambda, 4 lambda, take away minus kk, dotted with minus 1, 1. Okay, for my impulse. Then u1 take away u2 on the bottom. Well, u1 is 0, 0, u2 is minus 2u, 8u. So I'm going to take away 0, 0 from minus 2u, 8u. Again, I'm then going to dot all of that afterwards by minus 1, 1, my impulse direction vector. And so at that point, I'll just simplify it down. So if I now subtract the vectors, so I'm going to get 2 lambda plus k, and then 4 lambda minus k, dotted with minus 1, 1, and then plus 2u, and then minus 8u, dotted with again minus 1, 1. Then if I work out the dot product, so it's going to be minus 2 lambda plus k plus 4 lambda minus k over minus 2u minus 8u. And so I'm going to simplify a bit more. Okay, so I'm going to get minus 2 lambda, 4 lambda is going to be 2 lambda. Minus k will go to minus 2k over minus 10u. Now at that point, obviously I can sub in my expressions for k and lambda, okay. So if you remember, lambda is u and k is 4u, okay, so I'm going to sub those in. So lambda is u, so it's going to be 2u minus 2k. Now k is 4u, so it's 2 lots of 4u over minus 10u. And so that's going to simplify to minus 6u over minus 10u. And so hopefully you spot that's going to simplify down to 3 over 5. Because the u's will cancel and then we simplify the fraction. So therefore e is just positive 3 over 5. And that is and that's what they wanted me to prove. It's 3 over 5. And so there we are. So finally, I want to make a few final comments. The first thing I want to say is I actually haven't seen any exam questions, any past paper questions on this particular topic. So when you got vector collisions with vectors where it's not parallel to I or J, okay. So with these sort of questions we looked at in this section, I've not seen any past paper questions. There could always be a first time. So hopefully this has helped you prepare in case that comes up. But yeah, I haven't seen any exam questions on it. There's barely any textbook questions either. These are the only 3 questions that I've found on this topic. And so there we are. So again, hopefully this has helped with that. And actually, the final thing I want to say is you could, in theory, you can use the method we've done here with problems where it is parallel to I or J. So you could consider momentum to the vectors as a whole, and you can use this formula for E here, okay. This formula should always work, okay, with any problems like this with vectors, with in 2D collisions. But I don't recommend you do so. When it's parallel to I or J, I really do recommend you stick to the method we looked at in those problems, where you just look at the I or the J components on themselves, okay. Now we're going to be looking at some harder problems, which is going to involve angles of deflection, perhaps, and also a bit of harder trigonometry and algebra, right? But it's going to be pretty much the same idea of convert into 1D with the parallel parts, then momentum and restitution, and blah 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 blah, right? But before we look into those questions, I want to just look a bit deeper into angles of deflection, right? Now with vectors, it's very straightforward. I can just use the formula you would have seen from Corpuscle, where we can find the angle between the 2 velocities before and after by just using this formula here, okay? But when we're in sort of number form, okay, we're going to need to be a bit more cautious, okay. And so what I'm going to say for a tip is to find angle deflections, and this is for any angle deflection, even with walls, okay, which we looked at previously. Extend the original direction or velocity, okay. So I'm going to give some examples, right, how we can find out certain angle deflections. So in this example, let's say I have this sphere here, okay. Got the line of center like this, right. Then let's say originally it approaches the line of center here with initial angle alpha, okay. Then let's say it then rebounds like that, okay, and then an angle beta to the line of center, okay. So we always measure our angles from the line of center like this. So alpha and beta are just my angles before and after, okay. So hopefully happy with that. So this is like U, and then that's like V, okay, my before and after velocities. Hopefully happy with that scenario. Now, to find the angle deflection, it's not going to be this whole angle here, okay? It's not going to be alpha and beta, because that's not what the angle deflection is. Angle deflection is the direction we turn, so the angle we change direction. So again, if I use this tip here, I want to extend the original velocity, okay? So if I do it in different colour, if I extend the original velocity, it's going to look like that, right? Hopefully you can see that. So it's on the same path originally. And so the angle deflection, if I do it in a different colour, is going to be this angle here, okay? This is my angle deflection theta here. Hopefully you can see that, because that's because originally I'm going in that direction, then afterwards I'm going along here, and so I turn there, okay? So the angle between them is theta, my angle deflection. Hopefully you can see that, right? So again, if you extend the original vector, you can see the angle deflection. And so in this case then, well, again, because we're still on the original vector, if we consider the whole angle like this, then hopefully you can see we're on a straight line. Remember, angles on a straight line like this have to go to 180. So you can see here then, all three of these angles are on the same sort of line. They're on the same vector u. So theta and beta and alpha have to add up to 180. Okay, so 180 is all these three angles, alpha and beta add theta. Therefore, if we rearrange, we get the angle theta, my angle deflection to be 180, take away alpha, take away beta. Okay, and so that's my angle deflection there. Okay, if I was to work it out, and I can work out alpha and beta, because again, those are just the angles originally and then afterwards. And remember, we can just use SOHCAHTOA. When we got our components, we can use SOHCAHTOA to work out the angles alpha and beta, okay, if we're not already given them. So we can work out alpha and beta, therefore theta, the angle deflection, we can do this. So hopefully you can see that, right? Now, unfortunately, it's not always just going to be 180, take away alpha, take away beta. There's going to be different scenarios where it could be different. Let me consider this scenario here, okay? So now let's suppose the line of centers is vertical like this, okay? And so let's suppose originally we move like this and at an angle alpha here to the line of center, then it rebounds like that. And so then the angle to the line of center is beta here, okay? Again, you could convert this into a horizontal scenario if you wanted to. So if you were to flip it like this, you can see it would go like this at an angle alpha, and then there at an angle beta, okay? Now, no matter which so no matter which diagram you use, though, if it was to extend the original direction, so let's say here, the angle deflection is going to be here, right? Okay, that's all going to be theta. Okay, to work this out in many ways, but one way is to say, well, actually, if I work at this angle here, that angle doesn't have any relevance, but actually notice the angles beta, this orange angle, and alpha are on the same line. They're on the line of center. So if we do 180 take away beta, take away alpha, that's this angle here in orange. 180 take away alpha, take away beta. Okay, hopefully you can see that, right? Because again, they're on the same line. And so then for theta, well, again, we're on this line here. Okay, so again, the blue angle theta and the orange angle are also on the same line. So theta add the orange angle, so the 180 take away alpha, take away beta has to get me 180, right? Because again, the blue angle and the orange angle are also on the same line. Okay, hopefully you can see that in my diagram. So therefore theta I can rearrange to be 180 take away 180 take away alpha take away beta, and so if we simplify this we get theta to just be alpha add beta. Okay, and so that's the angle deflection in that case. So you can see it's different to the first example where it was 180 take away alpha take away beta. So unfortunately there's not one easy formula we can use. Okay, we are going to have to kind of visualize it a little bit, but yeah, as I said, the best advice is to extend the original direction, the original vector, and you should be able to see it clearly there. You might have to do a little bit of angle stuff, but there we are. By the way, to show you, this the same thing will apply in this diagram, right? Because it's exact same diagram but just rotated horizontally. If we was to extend the original direction like this, then you can see the angle deflection is going to be here, right? So all of that's again going to be theta. So therefore again theta and then the orange angle, which is 180 take away alpha take away beta, would have to add up to 180. Therefore you would deduce theta is also alpha and beta in the same way. Okay, so yes, the angle deflections can differ depending on the situation, which is why you should extend the original direction, and then you can see it for yourself there. But there we are. Right, so I've got this question here. So it looks really scary and ugly, right? How on earth are we going to get to that? But again, the main idea is we're going to do the same sort of techniques, right? So draw a diagram, then we're going to do momentum restitution. We convert it to 1D, and then we go from there. Okay. So yeah, let's draw the diagram first. Okay. So again, I'm going to draw a nice big diagram. So I've got my two spheres like this. So firstly, the line of centers here. Okay, now what am I told? So for A, the velocity I'm told makes an angle theta with the line of centers. So let's say A approaches the line of centers like that. Now I'm not told an initial speed, so I'm just going to call that U. Okay, and so the angle I'm told is theta. Okay, so it's quite general, right? I'm not really told anything really, but there we are. Right, and so then what about afterwards, where you can probably maybe presume it's going to then rebound like that, perhaps. Okay, and so this angle then, well actually, before I could call that angle beta, right? But notice I'm told something. The direction of motion of A is turned through 90 degrees. That is referring to the angle deflection for A. So the angle deflection is 90, which means if I was to extend my initial vector U, the angle deflection here is indeed 90 degrees. Okay, like that. So it's exactly 90 degrees. So actually we can work out, and we don't need to call it beta here. I can deduce what that angle is going to be, because again all three angles here have to add up to 180. So I can say that 180 is theta. Well, actually no, I can work out the missing angle to be 180 take away 90 take away theta, which is 90 take away theta. So I can immediately jump to this angle. I can be more specific than just saying beta. It's 90 take away theta. Okay, hopefully you're happy with that. Okay, because again all three angles here have to add up to 180. So theta add 90 take away theta, add another 90, indeed gets me 180. So hopefully happy with that, and hopefully happy that this is the angle deflection here, which I'm told is 90. Okay, between the two velocities like that. Right, okay. Now I'm also told B stationary. So originally there is no movement, okay, it's just standing still. So what about afterwards, right? Well, afterwards, okay, so if I look at A, obviously this will be, I'm not told any velocities. I'm not, so I'm just going to split up the components, right? So originally for A, we're going to go up by u sine theta, and then to the right by u cos theta. Hopefully happy with those components, perpendicular and parallel to the line of center. And then again, so then afterwards it's going to go up again because it's perpendicular. It's still going to be u sine theta. Okay, and we're also then going to go to the left, right? And so I'm going to call this a letter, right? Remember, we could say like v cos of 90 take away theta, right? We could say it like that, but I'm just going to call it a letter just to really simplify it. I'm just going to call that parallel component v, okay, for the parallel part afterwards. Hopefully you're happy with that, right? So lastly for B, because originally it's not moving, afterwards there's going to be there's only going to be a parallel part, so it's going to go to the right, let's say, right? It's going to be pushed to the right, as you can imagine. I'm going to call that speed w, okay, for that parallel part. There's no perpendicular part, because if there is originally no vertical part, no perpendicular part, there's still going to be no perpendicular part because the perpendicular part don't change. So there's only going to be a parallel part left, if that makes any sense. But there we are. And that's it. So at that point then, I've done my diagram. It's probably the hardest part, right? The diagram. So hopefully happy with that. Okay, make sure you go step by step if it's a bit confusing. But there we are. So A, what's the mass for A? It's M. For B, the mass is 2M. And so we're just going to jump to our techniques now, right? So firstly, we're going to look at the parallel parts. And so we're going to transform it into 1D. Okay, so I have my two spheres, A and B, M and 2M. So initially it's going parallel wise, so horizontally it's going to go to the right by u cos theta, sorry, and B is originally 0, right? And then afterwards, well, as we discussed, for A, it's going to go parallel wise, it's going to go to the left by V, like that. And then for B, afterwards, we said we're going to go forwards by W. And so there we are. So now we've got this 1D collision problem, so we can find V and W. So momentum firstly. So that's going to be A, well, mass is M, lots of the original part u cos theta. And then for B, 2M, lots of 0. So afterwards then it's going to be M, lots of minus V to account for the negative direction, right? And then 2M, lots of W. Now actually we can cancel the M's straight away. So we're going to get u cos theta equals minus V add 2W, and that is my first equation there. Okay, then restitution. So again, that's E, which is V2 take away V1 over U1 take away U2. Well, in this case, we have W for W take away V, but V's in the negative direction, so it's minus V. Okay. Then U1 take away U2, well, it's just going to be U cos theta, right? Take away 0. But then that's simplified to W plus V over U cos theta. Okay. Now, I'm not told what E is. I'm just told it's E, right? I'm not told a number for it. So I'm just going to have to make this equal to E. So therefore, EU cos theta is V add W. That's my second equation, right? Now, it looks ugly, right? We have thetas, U's and E's, right? but again, it's just simultaneous equations, right? It's going to be a bit more algebraic, but it's the same sort of process. So I've got these simultaneous equations, right? So I have u cos theta equals minus v at 2w. And I also have eu cos theta equals v add w. Okay, now there's probably many ways you can kind of solve it, some shortcuts you can do, but if we just do like the standard way, I guess let's rearrange the second one. So I just get v to be eu cos theta minus w, right? So then I'm going to sub v into the other equation to get w. So u cos theta is minus v, so minus eu cos theta minus w, add 2w, right? So we're going to get 3w minus eu cos theta to be u cos theta. Therefore, 3w, we can factor u cos theta out, and then we get e plus 1, right? Hopefully happy with that so far. Okay, I'm just rearranging for w. Okay, therefore divide by 3, I get w to be a third u cos theta of e plus 1. Okay, and there we are. Then I can find v by using this here. So therefore v is eu cos theta minus w, so minus a third u cos theta e plus 1. And so I can make that, I can factor u cos theta out of both terms. So then I'm going to get e minus a third e plus 1. Okay, hopefully happy with that factorization there. And then I can expand to get e minus a third e minus a third. So then that will go to u cos theta of 2/3 e minus a third. Okay, and then I can finally factor a third out. Okay, so v goes to a third u cos theta of 2e minus 1, and that's v in its simplest form. Okay, right. Okay, so I've copied my v and w, right? So obviously I found v and w, so v here I could replace it if you wanted to with a third u cos theta of 2e minus 1. And actually, if we just look back at the question, 2e minus 1 over 3, well, actually, our answer does involve that, right? A third of 2e minus 1. So it might be very nearly there. I'm on the right tracks. So that's just a little tip there, right? So I think I'm in the right position. So what do I do now, though? Right, so I found my v and w. Where do I go from here? So anyway, hopefully happy up to this point. So there's a bit of algebra, right? But hopefully you can see it's the same process we've been doing before. Okay. But where do we go from here? Well, it's talking about tan theta, tan squared. And again, I've got my sort of velocity triangle, right? So I have u sine theta, I have a third u cos of theta, lots of 2e minus 1. I have an angle here. So actually, I can probably just do a bit of SOHCAHTOA, and maybe I might get somewhere with these components here. So I'm going to draw out this triangle for A for afterwards, right? So I'm going to draw this triangle out here. So so this is the for the velocity afterwards. So this was the component v, right? And then we go up by u sine theta, right? And the angle, remember, was 90 take away theta, right? There we are. Okay. So that's literally just again just looking at my diagram. And so this is my vertical component, and that's my horizontal component, right? Then I've got this triangle here with this angle. Hopefully happy with that, right? So I'm just doing a triangle with my components for the parts afterwards for A. Hopefully happy with that. Hopefully happy with that. And also we know that V, again, is actually a third u cos theta of 2e minus 1. So, I can do tan, right? I can consider tan of 90 minus theta, right? Because obviously I can only do tan here because I've got my opposite and my adjacent length, okay? So if I literally just do the opposite over adjacent for this triangle I've got, okay? Again, hopefully you are happy with the triangle. The opposite is u sine theta over the adjacent of a third u cos theta of 2e minus 1. Well, actually, the u's cancel. So therefore, tan of 90 minus theta is sine theta over a third cos theta of 2e times by 2e minus 1. Okay, and we can actually simplify this even more. But firstly, if we're dividing by a third, we could just it's just the same as multiply by 3. So we have 3 sine theta over cos theta times by 2e minus 1. And then what do you notice? I have a sine over cos. That goes to tan. So I have 3 tan theta over 2e minus 1. Okay, and that's tan of 90 minus theta. Hopefully happy with that simplification there. Okay. Now, I can deal with this tan of 90 minus theta. This is a compound angle formula. This is a compound angle, right? I can use the compound angle formula, which is in the formula book, right? Here, right? Which hopefully you are familiar with from normal maths, right? Now, if I was to use that formula, so I have tan of 90 take away theta. If I use this formula, right, that's going to be tan 90 take away tan theta over 1 minus tan 90 tan theta. Now, you can see the issue here. If I was to use the tan compound angle formula directly, I'm going to need to find tan 90, which is undefined. So I can't use that formula directly. But how else can I express this? I can use sine and cos, right? So it's going to be sine 90 take away theta over cos of 90 minus theta. Hopefully happy with that. So I'm just using tan is sine over cos to express this here. And so now I can use the compound angle formulas for sine and cos to expand and simplify that way. So if I do that then, tan of 90 take away theta, if I just look at these two compound angle formulas, hopefully you can see that sine of 90 minus theta firstly will go to sine 90 cos theta take away cos 90 sine theta. And then if we use the cos formula, that's going to go to cos 90 cos theta plus sine 90 sine theta. And so hopefully you notice that if we evaluate sine and cos 90, this whole fraction will go to cos theta over sine theta, right? If you simplify it down, because sine 90 will go to 1 and cos 90 will go to 0, right? So you just get cos over sine. And this is actually just going to be the reciprocal or tan flipped, right? Because if tan is sine over cos, we flip it to get cos over sine. So it's 1 over tan of theta. And so there we are, hopefully happy with how I've got to that, right? So tan of 90 minus theta is also 1 over tan of theta. So I can sub that in, right? This is equal to 1 over tan theta. So therefore 1 over tan theta is going to be 3 tan theta over 2e minus 1. Therefore we can cross multiply like that, right? Cross multiply like that to get 2e minus 1 is 3 tan theta, 3 tan theta times tan theta. Therefore, 3 tan squared theta is 2e minus 1. Therefore, divide by 3, we get tan squared on its own to be 2e minus 1 over 3. And that is the result they wanted. Okay. Yep, that tan squared is 2e minus 1 over 3. Okay. There we are. Okay, so hopefully that made some sort of sense. So again, the first part of the question is going to be the same sort of idea, where we just apply momentum and restitution to find the missing parts V and W, the missing parallel parts. Then from there, we're probably going to need a bit of trig. So we might need to use the compound angle formulas to simplify any stuff, and a bit of trig identities, but then we should get to the result they wanted. Okay, so again, make sure you are confident with your trig stuff from normal maths. Okay, but there we are. Right, so now we've got this question here. I'm not going to read the question out because I'm giving most of the information on the diagram anyway. So I'm just going to draw the diagram out, but bigger, right? So I have my two spheres here, okay? So my line of centres here, okay? Then for A, you can see it's going to attack the line of centres here at an angle 45. So it's going to look like that. 45 degrees there. Okay, then afterwards you can presume that it's going to then rebound probably like that. Okay, the other way. Okay. And I'm also told with A, the direction of motion is deflected through an angle theta. So that's the angle deflection again. So the angle deflection is theta. So to visualize that, okay, so if I call the original speed u, if I was to extend it, you can see that this is the angle deflection, right? So that will be theta, right? And so therefore this angle then, well, it's going to be 180 because we've got angles on the line. So 180 take away the other two angles. So that will simplify to 135 take away theta, right? So 135 take away theta here, okay? And there we are. Okay. And I'm also then told B's at rest. So again, B has no movement originally. So what about my components then? Okay, so again, if I so this is my initial velocity, so it's going to go down, and then it's going to go to the right like that as well. So this is going to be u sine 45, and this is going to be u cos 45. Hopefully happy with my two components there, okay? And then afterwards, again, it's going to go down, again at the same perpendicular component of u sine 45. And then it's also going to go parallel, so horizontally, to the left. I'm going to call that, right, I'm going to call that just V. Okay, I'm not going to add any angles onto it. I'm just going to call it a letter V. Okay, not to overcomplicate it. So that's for A, right? So that's going to be A, and the mass of A is it's an identical sphere. Okay, they're identical, so their masses are equal. Okay, so I'm just going to call it M for the mass, and B's also can have a mass M because they're equal, they're identical spheres. Okay, so there we are. Now for B, again, if it's originally not moving at all, then it can only move parallel, so it's probably going to move to the right. Okay, because again, if the perpendicular part stays the same, there's no perpendicular part at the beginning, so there's also no perpendicular or vertical part at the end. So I'm going to call that parallel part W. And so again, at that point, we're just going to consider the parallel parts and transform it into 1D collision. So we have A and B, mass is M and M. Okay, so originally A is moving forward with U cos 45. And B is not moving at all, so it's going to be 0. And afterwards, A is moving backwards to the left with V, and B is moving to the right with W. Okay, so hopefully happy with that. Okay, so now we're just going to apply momentum and restitution. So momentum then, so M lots of U cos 45, and then M lots of 0 is going to equal M lots of minus V, because again it's going backwards, and then MW. And so we can cancel the M's. So therefore we get minus V at W to be U cos 45. Actually, we can evaluate cos 45, so we get minus V at W to be root 2 over 2U. Okay? And that's my first equation. Then restitution. So that's going to be E, which is V2 take away V1 over U1 take away U2. Well, in this case, V2 take away V1 is going to be W minus V. But again, V is negative direction, so it's minus V. And then U1 take away U2 is going to be U cos 45 take away 0. So that will simplify to W plus V over U cos 45, which again will further simplify to W plus V over root 2 over 2U. Okay, and so that's equal to E. Now again, I'm not told what E is as a number, it's just E. Okay, so there we are. So this is equal to E. So that means root 2 over 2 lots of EU, if I times across, is going to just be W plus V. And there we are. So again, I got these two simultaneous equations. I want to solve for V and W. So minus V at W is root 2 over 2U. And also V at W is root 2 over 2 EU. Okay. So I want to solve for V and W. Okay. So I can actually just add these equations, right? And then it gets rid of the V. So 2W is root 2 over 2U, add root 2 over 2 EU. And so that will go to root 2 over 2 U lots of E plus 1. Okay. Therefore, divide by 2. I'm going to get root 2 over 4, right? E plus 1. And that's W. Hopefully happy with that. Therefore, I can find V. I can sub it back into one of the equations. I'm going to sub V into minus V at W. It is root 2 over 2U. So I'm going to sub it into the first equation here. Hopefully happy with that. So therefore, minus V at W, the root 2 over 2. Oh, I should have included a U there, sorry. Root 2 over 4U. So root 2 over 4U of E plus 1. Is root 2 over 2U. So therefore V is going to be root 2 over 4U lots of E plus 1 minus root 2 over 2U. And then I can factor a root 2 over 2U out. And then that would be half E plus 1 minus 1. Okay, hopefully happy with that. Then I can just expand and simplify the second bracket. So I'm going to get half E plus a half minus 1. So that's going to be root 2 over 2U of a half E minus a half. Okay. And so then I can factor a half out as well. So root 2 over 4 U lots of E minus 1. There we are. Okay, so that's my expression for V there. Okay, so now I can go back to my diagram. Right, so I've added my two parts V and W here, my two parallel parts. If we look at the diagram then, I have V. I can substitute V in if you want to. So V is root 2 over 4 U of E minus 1, right? We worked that out. So I have my parallel component afterwards, and I have my perpendicular component afterwards, okay? So we can consider the triangle we get afterwards, okay? So the angle afterwards is 135 take away theta. Again, please don't get confused. This theta is the angle deflection. That's not what we're interested in. The angle afterwards is 135 take away theta. So we can again create a sort of velocity triangle with my two components here afterwards. So I'm going to draw that triangle out, okay? And again, we can then probably apply some trig to it, right? So for A afterwards, so if I do my line of center here, right, we saw that afterwards it goes like that, okay, at an angle of 135 take away theta. So my parallel part was V, and then it goes vertically like that. Now the perpendicular, the vertical part was U sine 45, right? Hopefully happy with that. Now V, again, if you remember, is actually root 2 over 4 U of E minus 1, okay? And actually we can simplify U sine 45, because sine 45 is root 2 over 2. So this is root 2 over 2 U. And so you can see I got this sort of triangle here then. Hopefully happy with that. That's sort of my velocity triangle afterwards with my two components and the angle here. So now I can apply SOHCAHTOA, right? So I can do tan, right? Because that's opposite over adjacent. So tan of 135 take away theta, that's going to be again opposite over adjacent. So the opposite is root 2 over 2 U over the adjacent of root 2 over 4 U of E minus 1, okay? And so the U's cancel, and if we now do root 2 over 2 divided by root 2 over 4, this simplifies to 2 over E minus 1, okay? But of course, this is not tan theta, it's tan 135 take away theta. So what we're going to need to do is again simplify that. So we're going to need to sort of expand that compound angle formula. So that's where we need to revisit my formula book, right? So my compound angle formulas. So I want tan of 135 take away theta. Tan of 135 take away theta like that. And actually, I can just use the tan compound angle formula. Sorry. Now, again, if you just look at the formula here, that will come to tan 135 minus tan theta over 1 plus, because it's the other way around, tan 135 tan theta. Okay. And so that again, that's just applying the compound angle formula for tan, which hopefully you've seen in U2 in normal maths. Okay, so hopefully happy with how I use the formula here to get to this. Right. So at that point I can simplify, because tan 135 is minus 1. So it's going to be minus 1 minus tan theta over 1 minus tan theta, okay? And if you want to simplify it, we can factor out the negative. So on the top, it would be minus 1 plus tan theta over 1 minus tan theta. Then we can absorb the negative into the bottom, into the denominator. So that will go to 1 plus tan theta over tan theta minus 1. Okay, so hopefully happy with that. So therefore that is tan 135 take away theta. Okay, in terms of tan theta, which is what they want in the question, right? So I can substitute that in. And so then, as we saw, tan of 135 take away theta is 1 plus tan of theta over tan theta minus 1. Therefore, we can say that 1 plus tan theta over tan theta minus 1 is equal to 2 over e minus 1. Okay, so we sort of need to rearrange for tan. Okay, so if I cross multiply, I get 2 lots of tan theta minus 1 is 1 plus tan theta lots of e minus 1. So if I expand, I get 2 tan theta minus 2 is e minus 1 add e tan theta minus tan theta. And so if I want to rearrange for just tan theta, then I move all the tans to one side. So 2 tan theta minus e tan theta plus tan theta is going to be 2 plus e minus 1. Hopefully happy that rearranging for tans on one side and the numbers on the other. Okay, then I can factor the tan out. So I have tan theta of 2 minus e plus 1 is 2 plus e minus 1. Okay, now it looks eerily similar, right? You might think they look like the same, but they're not, right? So don't try and divide stuff through. Okay, so we can simplify this. So tan theta times by 2 plus 1 is 3, take away e is 2 plus e minus 1, so it's 1 plus e. Okay, so they are different products. They look really similar, right? These two brackets, but they're not. So there we are. So hopefully happy with that simplification. Then we can just divide by 3 minus e to get tan theta to be e plus 1 over 3 minus e. And that should be the expression they wanted. Okay. Yes. There we are. We got there. Tan theta is 1 plus e over 3 minus e. So there we are. So again, hopefully you can see most of it was again the same sort of procedure where we solved for the parallel parts v and w by again by converting it into 1D, use momentum and restitution, and then we did a bit of trig at the end. So we drew a triangle for the components afterwards. Then we just used SOHCAHTOA, found tan, used a bit of trig identities, and then got to our answer. But there we are. Okay, so we've got this exam question here. Again, I'm not going to read the block of text. We're given the diagram here, right? But we need to show this expression for tan beta, right? It looks very ugly. But again, we're just going to do the normal process. Then hopefully we arrive to that, right? So, talking about the normal process, what do we do? Well, they've given me quite nicely what it looks like here, the velocities and whatnot. I don't think I'm told anything about angles or deflections here, so I don't need to do anything else. So I can just jump right into doing my components. So this is initially right. So you can see that's going to be perpendicular. So u sine alpha here, and then the parallel part, you can see it's going to go to the right, forwards here. That's going to be u cos alpha. Okay, right, and then afterwards, again, we're going to go down. Okay, and then we're also going to go across, forward like that. So my perpendicular part remains the same, so it's still going to be u sine alpha. And then parallel, well, I'm just going to call that a letter, right? I'm going to call that, just say, a letter V, right? As I usually do. So that's my parallel part for A. So that's all the parts for the first sphere, okay? They call it S, not A. My apologies. But that's the first sphere. Now for the second one, they've told me it's at rest. So, and you can see that here, there's no speed, there's nothing going on with the second one. So if it's at rest initially, it's just afterwards going to move parallel. It's going to move just to the right like that, right? You can imagine it's going to be pushed to the right, forwards by the other sphere. Again, that's because if there's no parallel part before, there's no parallel part afterwards, so no verticality. So it's only going to go across parallel. I'm going to call that part W. Okay, and there we are. So those are all my components there. So now I can do my usual techniques of considering just the parallel parts. Okay, parallel components, my parallel speeds, if you will. Again, I'm going to do it in 1D now. So what do they call the spheres? They call it S. I'm going to call the other one, I don't know, Q, let's say. So S has mass M, and the other one has mass big M. Okay, they're just really trying to confuse me here. So different masses. Okay, one's little m, one's big M. Okay, so hopefully happy with that. Now for the first one, as we just done, the initial parallel part is U cos alpha going forwards. And initially the other one's at rest. Then afterwards, it's going forwards with this speed V. And the other one's going forwards with speed W. Right? There we are. And so again, at that point, I can apply momentum and restitution. So momentum firstly. So that's going to be M lots of U cos alpha, add big M lots of 0 is little m lots of V, add big M lots of W. Now I can't cancel the M's because they are different. Okay, so I'm gonna have to leave them where they are. So MV add big MW is MU cos alpha. And there we are. Okay, can't do anything more to that. Then for restitution, so that's going to be E, which is V2 take away V1 over U1 take away U2. Okay, well in this case, V2 take away V1 is going to be W minus V. And I don't need to negate any of them because they're both going in the positive direction forwards. Then U1 take away U2, that's just going to be U cos alpha take away 0. So that'll go to W minus V over U cos alpha. And again, I'm not told what E is, so I'm just going to leave it as E. Okay. So therefore, EU cos alpha is W minus V. And there we are. So I've got these simultaneous equations. So W minus V is EU cos alpha. And then I also have that little mv add big MW. It's going to be mu cos alpha, I believe. Yep. So I've got these simultaneous equations, right? Again, they look awful, but again, don't worry about the algebra. We just do the normal process. So we solve with the W and V. Actually, we can immediately rearrange the first one. We can rearrange the first one to get, let's say, W to be V add EU cos alpha. Then I can sub that into the second one. So therefore, I'm going to get the MV add big MW, which is going to be V add EU cos alpha. It's going to be MU cos alpha. So if I expand that, I get MV add big MV add big MEU cos alpha equals MU cos alpha. Then I can factor the V out. So V lots of little m and big M. is going to be mu cos alpha, take away big M EU cos alpha, right? Hopefully happy that rearranging. So I can simplify this. I can factor U cos alpha out. So I have M take away big M E. Okay. And so therefore I can then divide by M and big M to get V to be U cos alpha of M minus ME over M plus big M. Right, one awful expression, but there we are. Okay, now we don't need to find W here. We could find W, but we don't really need it because look at what the question is asking me to do. It only wants me to find tan beta is some lots of tan alpha. So actually that only involves the angles for the first sphere, right? So I only need to find V because W is for the second sphere. So I only need to find V for the first one because I only want to consider the first sphere. So actually I could just leave it there, okay? So that is V, right? Right, so we're back to our diagram then. So now that we've found V, so we have the component V, we also have the component U sine alpha, right? So we have the two components afterwards. So we can consider the sort of the triangle we get right afterwards, right? So we're going to get this triangle here. So I'm going to draw that below. So for the first sphere S afterwards, we get this sort of triangle. So again, if this is like my line of center, as you can see, we're going to go, we went like this at an angle beta. So first we're going to go across like that. That's my parallel part V, and then my perpendicular part downwards, which was U sine alpha, right? Hopefully happy with that. So I can only do tan right here because I've got my opposite and adjacent. So tan beta in this case, again, that's opposite over adjacent. So in this case, the opposite length facing beta is U sine alpha, divided by the adjacent side V. Hopefully happy with that so far. But of course, we know what V is. So it's U sine alpha divided by V, which is this nasty fraction here. U cos alpha, M minus big ME over M plus big M. So I'm going to divide by that. The U cos alpha of M minus ME over M plus big M. Okay. Now, of course, when you're dividing like this, I can just do KFC, flip back to GCSE, keep flip change. So I'm going to do U sine alpha times, then I'm going to flip the fraction. So I'm going to get M plus big M, and then U cos alpha of M minus M E. Okay, and so then if I times across, I get U sine alpha, lots of M plus big M over U cos alpha of M minus M E. Right, and then I can do a little bit of simplification. The U's cancel, and I get sine over cos of alpha. So that will go to tan alpha, right? So we get tan alpha, lots of M plus big M, over M, little m minus EM, if I just do it the other way around. So E big M. Hopefully happy with that simplification, and that's tan beta. And actually, that's the expression they wanted. Okay. Here, right? So tan beta, M plus big M, lots of tan alpha over E M minus E big M. So we get that horrible expression there. Okay. So there we are. And by the way, it's a good idea not to work out W because we didn't need it. So don't do any unnecessary work, okay? But yeah, it looks scary, right? But hopefully you can appreciate that again. we just did the usual method. So we found the components, then we converted into 1D with the parallel parts, then used momentum restitution to solve V and W in the usual way, and then we did our triangle and then did a bit of trig and SOHCAHTOA. But there we are. Okay, then I'm told that actually little m is E lots of big M. And so I need to show that the direction of motion of the two spheres afterwards are perpendicular. Okay, so obviously they've asked me to do part A. They asked me to show this result for a reason. And so let's try and substitute this in. Okay, M is E big M. So if I do that then, if M is equal to E big M, therefore tan beta in that case is going to be M, which is E big M, plus big M, lots of tan alpha, over little m, which is EM, minus EM. Oh, hang on, we've got a big issue here. These will cancel to get me 0. So I'm going to get EM plus M tan alpha divided by 0. Oh dear. Can't divide by 0, can we? But actually that tells me something quite important. Because it's tan, that tells me it's undefined, right? What value for the angle gets me undefined for tan? So tan beta is undefined because you can't divide by 0. So what does that mean? What value for the angle gets me undefined value for tan? Hopefully you're thinking that is 90 degrees, right? So therefore beta must be 90 degrees, okay? Because that's when tan's undefined, right? It's got that asymptote on the graph. And so hopefully you can see then it's going to be a right angle. So beta's 90. Afterwards, we're going to move at a right angle to the line of centre, okay? So therefore I'm going to say that therefore afterwards the first sphere moves perpendicular to the line of centre. And actually, how does that help then? So I'm told to show that the direction of motion of the two spheres are perpendicular, right? So they're going to be perpendicular to each other afterwards. Well, that makes sense actually, because as we just worked out, the first sphere is moving perpendicular to the line of centre, but actually we also know the second one is moving parallel. So actually you can see then, if one's moving perpendicular and the other one's moving parallel like that, then their two directions are going to be perpendicular to each other. And there we are. So the two directions are perpendicular to each other. So therefore I'm going to say, as the second one, the second sphere is moving parallel to line of centres, because one's moving perpendicular, one's going to move parallel, so they're going to look they're going to be looking like that, right, at 90 degrees to each other. Therefore the two spheres move perpendicular to each other afterwards. And there we are. Okay, so we've got this final question here, right? Again, I'm not going to read the question out. I'm giving the diagram that basically tells me everything I need to know anyway. And so again, part A, I need to show this speed afterwards. But we're just going to be doing the same method, right? And then once we've done our method, so we look at the parallel parts, do momentum and restitution. Once we do that, we should be in a very good position to do what they want us to do. So as I said, I've got this diagram. I just copied it here, and so basically I can just annotate the diagram, right? So what do? I just do my components. So firstly for A, obviously this is the perpendicular part, so that's going to be u sine alpha, and then likewise parallel we're going to go to the right, and that's going to be u cos alpha. Okay, and then afterwards, again we're going to still continue going downwards, and that's still going to be u sine alpha, because again the perpendicular parts don't change. And then we're also going to go to the left, right, parallel wise. So that's going to be, I'm going to call that a letter V. Right, I'm just going to leave it as a letter. What I also know in this particular case is that I'm told that actually this whole angle is a right angle, it's 90 degrees. And hopefully you can see then that that this angle then afterwards, where we can just do 90 take away alpha. Okay. Okay, I'm not going to use the angle just yet, but when we get to it, we have this expression for the angle here. So hopefully happy so far. Okay. Then for B, it's originally at rest. So afterwards, it can only move parallel. So horizontally, it's probably going to move to the right. Okay. I'm going to call that part W. Okay, and so now in a position I can do my parallel parts and then apply my usual stuff. Okay, so I have A and B. A has mass m and B has mass 3m. Now the parallel speeds, u cos alpha to the right, firstly for A. For B, it's at rest, so it's at 0. Then afterwards, A is moving to the left by V, and B is going to move to the right by W. And so at that point, I can apply momentum and restitution. So for A, it's going to be m lots of u cos alpha, add 3 m lots of 0 for B, then afterwards it's m lots of minus 3 because it's in the negative direction, and then 3 m lots of W. Okay, and then we can cancel the m's straight away. So therefore we get minus V, add 3W to be u cos alpha. Okay. And so then restitution is next. So again, that's E, which is V2 take away V1 over U1 take away U2. And so in this case, that's going to be W take away minus V. Again, it's in the negative direction, backwards. Then we're going to get u cos alpha take away 0. So that will simplify to W plus V over u cos alpha. And so that's just equal to E. Again, I'm not told what E is exactly as a number. It's just E. So I'm going to just say that if I times across, I get EU cos alpha to just be the V add W. And so again, I get these simultaneous equations here, right? So I have V plus W is EU cos alpha, and also minus V add 3W to be U cos alpha. Okay. So to solve these now, I can immediately spot I can add the equations to get rid of the V. So 4W is going to be EU cos alpha, add U cos alpha. And so that'll factorise to u cos alpha lots of E plus 1. Therefore, divide by 4. I get W to be a quarter u cos alpha lots of E plus 1. And actually, I think we should have done the first part then, right? That's the, yes, that's the expression we have. That's the speed of B afterwards, right? Because remember, afterwards for B, the only part is the part W, right? W is the speed, okay, because it's only going in one particular direction. So there we are, that's great. So then the second part says show that E is greater than the third, but I also note it then wants me to find this sort of inequality for tan alpha. Now remember, alpha is the angle for the sphere A. So I'm probably going to need to find V as well. Okay, so V being the parallel part for A. So if I continue solving this, right? If I continue solving, and then we'll see how we can go from there. So I know what W is, so I'm going to sub that back into one of the equations. Let's say I substitute it into the first one here. So that's going to be a V at W, which is going to be a quarter U cos alpha of E plus 1. It's going to be EU cos alpha. And so at that point, V is going to be EU cos alpha, take away a quarter U cos alpha, lots of E plus 1. Hopefully happy with that. And then I can just factor stuff out. So U cos alpha, lots of E minus a quarter of E plus 1. Then I can tidy up the bracket, this bracket here. So if I expand, that's going to be E minus a quarter E minus a quarter. And so lastly, we get U cos alpha to be U cos alpha lots of 3/4 E minus a quarter. Then finally, we can factor out a quarter. Okay, so a quarter U cos alpha of 3E minus 1. And there we are. Okay, we got there. So that's my expression for V. This is where I think back to kind of what we did in AS with 1D collisions. What we've essentially done so far is just a 1D collision problem, right? That's what we've been doing this whole time. We've just been converting this into like a 1D situation. So one of the sort of techniques or things we looked at with 1D collisions is we can sort of get inequalities by considering the direction it's going in, right? So if we know for sure V's going backwards, that has to mean it's going to be a positive answer, okay? For example, if we had -2, if we got a negative result for V, that would tell me indeed I'd have to flip and reverse the direction, okay? So I need to consider the sign of my answer, okay? So if I'm saying V is going backwards to the left, well, actually, if I look at what they've given me, it has to move to the left. I'm told where the trajectory is. I'm told where it's going to move afterwards. It has to, the particle has to move to the left. It can't move to the right. That's not what I'm told. I'm told for definite it has to move to the left because I'm just given the diagram, right? So that has to mean V must be positive because I do not want to flip the direction. So it cannot be negative, okay? Because I'm essentially told that. So it must be going to the left here. Hopefully with me there. We did look at that in chapter 4 with 1D collisions, but we can apply it here as well, right? Because we've got a 1D situation. Right, hopefully happy with that. So indeed, parallel has to move to the left, right? Okay, so that forces V to be greater than 0. So A must be moving to the left. After the collision. Therefore, V must be greater than 0 to ensure that it indeed is moving to the left, okay? Therefore, we can set the whole thing greater than 0. Okay? And actually then, we can actually divide by the quarter U cos alpha, okay? And so we get 3E minus 1 greater than 0, which is what we kind of wanted to get to, right? Now, the reason we can do this, firstly, U is a speed quantity. So U is a speed, so that forces U to be positive, because speed is positive, right? So U is positive, okay? A quarter is obviously positive. Now, what about cos alpha? Now, we're told in the question, I believe, alpha is between 0 and 90. Now, if you think about cosine, the cosine graph between 0 and 90 here is also positive. So we can confirm to ourselves that indeed this whole expression, a quarter u cos alpha, is positive. Okay, so we can keep the inequality sign where it is. We don't need to worry about if it's negative, are we going to flip the inequality, because we're divided by positive quantity. Okay, but there we are. So we get to this point, and therefore e is greater than a third. And there we are. We got to what they wanted. Okay. But yeah, I think it could be fairly tricky. That part could be, I think. But again, because we convert it into a 1D problem, we can do the same sort of techniques that we looked at in that chapter. Okay, in chapter 4. Okay. So we can do the same sort of stuff. Okay. But there we are. Hopefully that made sense. Okay. Now we've got the final part. So now we need to show that 0 is between tan alpha and it's less than or equal to 1 over root 2. Again, how on earth are we going to get to that? Well, the key giveaway is talking about tan alpha. Okay. So we're going to need to consider the angles, right? And so what do? Because we know what V is, okay, we have our two components. We can now do our sort of velocity triangle, and then we can take tan and then see how we go from there. So I'm going to draw the triangle of the velocity afterwards with these two components. Hopefully you're with me here. So we get this triangle here. So it goes down like that. That's going to be V, and then we're going to go down by u sine alpha. And the angle, if you remember the angle for this sort of triangle afterwards is 90 take away alpha. So that's going to involve the alpha, right? Okay, so obviously we're going to want to consider tan then. So tan of this angle 90 minus alpha, that's going to be opposite over adjacent. Okay, which is going to be well, the opposite side is u sine alpha and the adjacent is v. Now if I sub in what v is, so u sine alpha divided by v, well, v is a quarter u cos alpha of 3e minus 1, so a quarter u cos alpha 3e minus 1. And then we can simplify this a little bit, right? So firstly, the u's cancel. If we divide by a quarter, we can just multiply by 4. Sine over cos is tan. And then we can divide by the 3e minus 1. Hopefully happy with that simplification there. And so this again is equal to tan of 90 take away alpha, the angle afterwards. So again, this whole thing is the components afterwards. Okay. Hopefully happy so far. Now, of course, again, as always, we're going to want to sort of simplify this compound angle, expand it, if you will. How are we going to do that? Well, we can use the formula book. So again, these standard identities when we've got compound angles. So again, we want to simplify tan of 90 take away alpha. Now, you won't be able to use the tan one because you're going to need to plug in tan 90, which is undefined. To get around that, we can use sine over cos, okay? Then we can use the formulas for sine and cos respectively, as we've looked at with a few examples already. And so if we apply the formulas, hopefully you're happy to see that this will be sine 90 cos alpha, take away cos 90 sine alpha on the top, over cos 90 cos alpha plus sine 90 sine alpha. And then we can just we can evaluate sine and cos of 90, right? If we work all that out, you should get cos alpha over sine alpha, because sine 90 is 1 and cos 90 is 0. So hopefully happy with that simplification there. And actually we can further simplify this to the reciprocal tan, right? It's tan flipped, because tan is sine over cos, cos over sine is the reciprocal. And so we get to this sort of identity here. Alright, hopefully you're with me here. Hopefully that made sense. So again, I use these standard formulas, which you should be comfortable with from normal maths. Right, I'm going to sub that in then. So tan 90 minus alpha is 1 over tan. Again, I just want everything in tan, because that's what the question wants me to get to. So this is 1 over tan. Therefore, 1 over tan alpha is equal to this. So 4 tan alpha over 3e minus 1. Therefore, if I cross multiply, I get 4 tan squared alpha is 3e minus 1. Then I want tan alpha, right? So firstly, if I divide by 4, tan squared alpha is 1/4, 3e minus 1. And so therefore, if we square root both sides, we finally get tan alpha to be, it's not going to be plus or minus, it's just going to be the positive root of this, right? 1/4, 3e minus 1. Now, it's not going to be plus or minus, it can't be minus, because tan alpha can't be negative, because alpha is, alpha's between 0 and 90. So again, if you consider the tan graph between 0 and 90, it's again positive. So tan alpha is going to be positive, okay? So we do not consider the minus case when solving. So it's just positive, okay? So hopefully happy with that. And so then we can just simplify the roots. That's going to be a half root 3e minus 1. And so there we are. So that's my expression for tan alpha, okay? But remember, the question wants me to get an inequality, okay? It wants me to deduce that tan alpha is between 0 and 1 over root 2. Now, what's the key difference here? There's no e involved, okay? So now I'm thinking I can use part B, that e is also greater than 1/3, and that will actually probably get me inequalities, right, for tan alpha. So I'm going to use e is greater than 1/3 from part B to try and find inequalities for tan alpha, okay? So hopefully you're with me here. Right, so I've got this equation for tan alpha, but I also know that e is greater than 1/3, okay? But of course, that's not the full complete range of values of e, because if you remember, also e is always between 0 and 1. So actually, we can be more specific and say, well, e is greater than 1/3, but then e is also less than or equal to 1. So e is sandwiched between 1/3 and 1 like that. So we actually have this full inequality for e here. Okay, hopefully happy with that. So now I can effectively use this inequality for e to find the inequalities for tan alpha, right? Now, there's many ways you can kind of do this. I think probably the safest way is to start with this inequality for e, then work our way up to get this whole expression here, okay? So we want a half of root of 3e minus 1. So if we know e is between 1/3 and 1, therefore if we triple it firstly, 3e is going to be between 3 and 1. Then if we subtract 1 to both sides, we get 2 and 0. Okay, hopefully happy with that. And then if I root both sides, I get root 3e minus 1 greater than less than or equal to root 2, less than or equal to root 0, which is 0, right? Hopefully with me so far. And so the last thing I need to do to match this equation is to times by half, right? So lastly, if we multiply everything by half, I get a half root 2 and then 0 again, right? And so that's tan alpha. So therefore, that is exactly the expression for tan alpha. So tan alpha is between root 2 over 2 and 0. Okay. And that should be the inequality they've got. Okay. Yes, it's correct, but they've wrote it in a different way, ever so slightly. 1 over root 2, if we was to rationalise that, that would be root 2 over 2. Okay, so indeed we have the exact same inequality that they've got, but just written in a slightly different way. Okay, so yes, we have the inequality the question wanted me to obtain.